Right. Good morning, everyone, and welcome to the second workshop on conventional 3D vision. Um, Today we have an exciting program, and this is joint work with Wolfgang Hedrick, Peter Vajda, Natalia, and a group of fantastic students and collaborators who have worked so hard to prepare the program. Today's program will start with very exciting talks. This is an overview of the program starting from 8:50 to 6 p.m. We have a fantastic lineup of speakers, Professor Andre Fidelity, Katarina, Minu, Jandru, Srinath, and Jiao Jun and Angela Dai. So we have also two workshop challenge that has been running, a 3D Combat Challenge and also RESEC that will be covered at 3 p.m. today. We have two breaks as well as poster sessions that are going to happen at 10:10 as well as at 3:15 to 4 p.m. This will happen at the ARC building for at the exhibition hall. And there are in the program also, there are 12 papers that has been accepted in the program. 7 of these will be orally presented, and this will be covered at 1:35 to like 3 p.m. right before the workshop challenges. And this is basically the summary of the workshop. We have 7 35 minutes talks, 2 challenges, 2 breaks, 45 minutes panel discussion towards the end, oral spotlights or oral presentations for 90 minutes, and a total of 75 minutes of poster presentations. But please note that this poster presentation will happen in the art building because this is how it has been organized here by CVPR. Thanks, everyone. And with that, I would like to introduce Professor Andre Vitaldi. Professor Andre is a professor of computer science and machine learning at the University of Oxford, and he leads the visual geometry group since 2012. His current work focuses on generative AI for 3D computer vision, for generating 3D objects from text and images, as well as the basis for image understanding. He's author of more than 200 peer-reviewed publications in top machine learning and AI venues. He's a recipient of the recipient of Mark Abraham Prize for selfless contribution to computer vision community, and the Test of Time Award by the ACM for his open source contributions, and the Best Paper Award for the computer and vision and pattern recognition conference. And today he's going to talk about structure and composition in 3D AI. Please join me to welcome Andre.
So we started some, I don't know, yeah, maybe not all the time yesterday.
Yeah, I don't know what happened.
And on the table, we started. So what?
And folks also confirm that the Zoom share is working, please. Hello. Nothing. Is it working? It seems I'm very good at attracting technical issues. Yesterday was also not working. Something was also not working. So I guess it's yes.
Check. Weird. It's hitting the board, huh?
Yeah, but I wonder about Zoom. Does that work? Yeah, do that.
Same thing happened all day yesterday and they had to restart it like several times during the day.
Well, it's a good thing we are 5 minutes early. I guess 2 minutes early now. This showing some levels, is it?
Yeah, it's hitting here. It's also hitting that, but it's the actual speakers now. They shut off. So, but I put a message in and they're going down the line and, somebody has to call somebody and all this, and then somebody pushes a button somewhere.
In the Vatican.
Oh, yeah.
In the Pope. See, fish.
Yeah.
Speaker. Speakers only and that's starting with speakers. I can shout, that's for sure. The question is, will people on Zoom be able to hear me? I can turn on the audio of my computer.
I think if the mic is on, they should be able to.
Oh, really? Okay.
Yeah, the mic.
The mic is on.
Okay. Yeah. So should I also share screen here? Oh,
Hey,
great.
yeah.
That's so much now. I'll do a little bit. Perfect. Okay, perfect. Okay, don't need to show anymore. Such a lot of opportunity. Okay. Hello. Aha.
What?
Shouldn't have said that. Okay. Right.
Okay.
Should I shout then and just carry on? Okay. Wait, it's working again. See? Yes. Just this terrorizing me shouting. Okay.
I'm gonna wait a couple more minutes just to see.
Let's see what happens. Aha. Exactly.
Somebody's playing in German.
Yes. Okay. Right. So I'm here today to try to talk to you about structure and composition into the AI. I have modestly put composition in parentheses there because there would be some of it, but not too much of it, I think. All right, so I would like to start by just noting maybe the obvious. So machine learning and 3D computer vision are really coming together now. So we have new ways of representing the 3D world. For example, near-reference fields, mind geometry, and learning from the point of representation of the 3D world. We have tools for 2D generation, so you can take a bit of text, like a house with a bit of clouds on a hill. Okay. Or you can even take a single image or maybe a video here and start the animals from that. And of course, this is something that involves 3D geometry, but it's also not something you can do without suitable clients. So that's where machine learning really helps by combining with geometry, which is just algebra, if you like, statistical information that we require to solve this class of problems and more. But I would like first to discuss how we can go beyond just 3D construction. So 3D construction, for example, with NERF is great, but what else can we do with it? And how can we particularly put some structure? So maybe we can do some interesting things with it. So just as a reminder, what I mean by 3D construction here, I really mean 3D construction through optimization. So suppose we're given a model M of the scene, you think of that as NERF, that is to say a radiance field. In these days, you would be using Gaussian splatting. You have an image, about several images I here, that you capture to try to get information about your scene. And then there is a rendering function which is differentiable. So given the model M, given the camera CI, you can render in a differentiable manner the image that you obtain from the 3D model, and then you can compare that to the image you get from reality, and you can cast that as an optimization. So you can set up an optimization problem in which you try to make the rendered image as similar as possible to the image you measure. And by minimizing this error with respect to the model, you're going to get your 3D construction. Right? Everybody understands that. This was made very, very popular by NERF, because then you have this combination of learning the different representation and this differentiable optimization. Sorry, this differentiable objective that you can optimize using a gradient descent, for example. But once you have that, for instance, suppose that now you have a network here that can extract some features from your image. This could be some centralized features like Dino, could be a segmentation network, something like that. So you can take your input image, you can pass that to the network, and off you get with some features. And what you can do is you can add the features as additional channels in your image, and you can extend your model so that when you render it, not only you render the RGB colors of the pixels, but you also render the values of the features. And now you solve the same exact division problem, but now you, again, start not just the RGB channels, but also the feature channels. This is very, very simple. But in this manner, what you can do is you can essentially fuse the information that extracts on an image by image, or an image made with image basis into a single coherent 3D model. All right? So this is a way of fusing 3D information into a single 3D construction. So why is that useful? Well, because you're lifting this information in 3D and you're making it more consistent. So this is an example of neural feature fusion fields. So this is a paper which is already 3 years old now, where we start with this idea and got using these Dino features, which are these accessorized features that you can extract from each frame independently. And so you can see here a PCA version of those. And the idea here is that the colors should correspond to different semantic bits of the scene. And you can see that these are low resolution to some extent and also really consistent, viewpoint consistent, which should not be the case because the semantic of what you're looking at the image should not depend on viewpoint. But if you fuse the features in 3D, then they get cleaned up quite nicely, so they become less noisy, they become more performant. You can do some things with that. You can start to have some decomposition of the 3D model into different parts. So here you see the full reconstruction, it's just a nerve. And here you can see the foreground, which has been extracted completely automatically by using this set of class features. So Dino features, they're not trained using labels, they're trained just using images. Even so, because the features are actually very good, once you use them in 2D, you can get something like automatic segmentation of this component. So you can get foreground and background in a separate manner now. Okay, so that's one example of fusing features in 3D. But of course, you can fuse any features. So here, suppose contrast lift that was released last year, where we look at the same problem, but in this case, what we wanted to fuse are not semantic features like Dino, semantic labels, but rather segments which characterize instances that we observe in your frames. And these are essentially just instance segmentations, if you like. So these are not necessarily consistent across different frames you capture. So you can see here that the segments, they're sort of stable, but not really. And in particular, the colors, which is the segment identity, actually flashes through time. That's not what you want, because you know that the object is always the same. It's just that because you're detecting them independently of the frame, they're not consistent. I confuse the detections using contrastive lift, and now the detections become better, more global if you like, and also they don't flash anymore because we resolve sort of inconsistency that you get by processing things one frame at a time. So just again to give a sense of how this works. So here are two frames, and you run your instance segmentation system, so you get frame 1 and frame 2. You get sort of the same object, but the colors are different because the labels are not consistent. There's instance indices, the object 1 and the object 2. And maybe on the image, this one is object 2 and this one is object 3. So they don't match. So you can reconstruct the 3D model, assign labels to your 3D objects, but now you have a problem that when you want to match your 3D model, when you measure, every time you do that, you need to find a permutation that rearranges the labels in such a way that are compatible with the label set off from your 2D segmenter. Now that's possible, people have done it, but it's also a little inconvenient, a little slow, because every time you need to compute this permutation matrix, every time you compute your loss, so that's annoying. So what we did in contrastive lift was we formulated this in a contrastive fashion. So you see here we have selected a three-dimensional point, the star, and then we select additional 2 points, one on the same object and another one in a different object. And if you compute the distance between the embedding you're trying to learn, so here we associate with each 3D point picture vector, which is supposed to be characteristic of that particular object instance. So if you compare those instance vectors like that, you see that the difference between them here is small. That's why this is black. That means that the difference value between the features you get here and there is small. That's because they belong to the same object instance. But if you go across the instances, that's actually large. If you think about it, this property of labels being either small or large, the distance between labels to be either small or large, holds in 3D space, but also holds in a sort of invariant manner in each one of the views you are extracting. So this now is a loss that so you can compare this sort of map, this sort of relative map to the relative map you get in your images, and that's actually going to be permutation invariant. And that's nice because then things learn faster and better. So the data point here is that if once you have used your semantic labels this way, then the performance that you get actually improves. So this is the case when you integrate 3D computer vision and you add it to your 2D segmenter, which is again done on a frame-by-frame basis, actually you get quite a big boost in terms of detection performance. So this is a case where the vision really helps 2D machine learning development. And you can carry on like that and be creative. So for example, you can use language features. So here we have a way of taking 3 features and embedding them in the space. So you might be familiar with the results like those. Kanazawa's group have some great examples of that already. But what you see here is that with this new thing I've developed, which is called nested neural feature fields, you're able to be much better sensitive to composite queries or queries that really try to combine a bunch of different content using language. So for example, here you can say green toy chair, and only the green toy chair lights up. Then you can go and say, I want the chair legs, and only the chair legs light up, etc., etc. And so this is obtained by essentially so we found a way of summarizing different resolutions or different semantic scales of the features into a single three-dimensional embedding that then can be called very, very efficiently once you have your text in grid. So if you're interested, please have a look at our paper. Okay, this is another example in which language now in this case helps you to decompose a scene into different parts, different components, at different semantic resolution levels, but also different sizes, physical sizes. Okay, so moving on. Next, I would like also to discuss a bit the issue of motion. So when it comes to this 3D reconstruction, they work very well if you're seeing static, right? But it's actually not the case if the scenes contains some dynamic content, for example, say the cat in this case. So this is a video from Kanazawa's group where she shows the difference between what she calls casual captions. So this would be capture that you may be capturing with your cell phone, as opposed to the sort of existing capture for dynamic scenes that people would like to play with in papers. So what you'll notice is that in both cases, the scene is actually dynamic. So I think this guy is going up and down. This is like the cat is alive, so things are changing over time. But the difference is that here, the dominant motion is the motion of the object. Here, the dominant motion is the motion of the camera. So it turns out that doing 3D reconstruction, or I should say for 3D reconstruction, is much easier here than it is there. Just because the camera motion is dominant, so it's more easy or easier to train things like triangulation. But really, when it comes to reconstruction in a more realistic setting, this is still very, very hard. I think that in the future of the divisions, we need to move in this sort of idea of reconstruction, and to do that, we're going to need to have better tools for tracking motion. So one thing we're doing is developing a new class of trackers. So here you see an example from Code Tracker, which is just actually a lot of work, but it's a transformer that is able to track together hundreds of individual points and get state-of-the-art results in tracking performance, or at least now about comparable to other similar class tracking the same class. But the point here is really that now it's possible to track these points much better than it was possible a few years ago. And I think these are tools that will help us a lot to understanding the dynamics. So what do we care about dynamics in composition? Well, if you think about it, when it comes to explaining or modeling the motion of objects, then you're not just explaining the motion of single thing you see in one video, but you wanted to explain the motion of family of objects. For example, humans, or maybe all mammals of different type, like all horses or all lions. And you can do that by developing a lot of models, like for example, SNPL and small. And that's fine. These models work great, but it also takes a lot of effort to be able to build them and train them. So what we wanted to do was try to open up the computer vision, in this case, in fact, for computer vision, so understanding object categories that are dynamic and animated in a way which is not restricted just to a few categories that you need to train by collecting quite a bit of manual training data for that, manual weights for that. So the idea here was to scale learning by using internet data instead. All right, so this is a set of works that we have been developing over the course of several years now, in Oxford, mostly in Oxford and Stanford. And there is in fact the latest of such works, which is Farm3D, which is sorry, racist. Yeah, learning to be on the web. It's out here. It's going to be presented here as CPR. So if you want to have a look at this, go to the course session and check it out. So anyway, so this is a long series of works where we are trying to develop this system that are able to learn dynamic object models on internet images that are not restricted to just a few object categories. So the way this works at a very high level is actually quite simple. So we use what we call here a photogeometric autoencoding approach. What this means is that you have a collection of images as inputs, then you have a network that we call a de-renderer that comes up with a set of automatic and geometric factors that explain the content of your image, so shape, material, motion, light, and camera. And then you have a rendering function, which is basically just deterministic, if you like, or manually abstracted, that takes these factors and reproduces the image content as closely as possible. And now you can train that just as if it was on GS. Okay? So our reconstruction loss, and this means you can train that without limits. Now, of course, this is easier said than done. So there's quite a bit of work we need to do to be able to do that on scale and robustly enough. So one thing we did here was, first of all, to come up with a way of modeling the motion, the shape of any object. So we start from volumetric space here, which is the embed space that is differentiable. It's initialization that gives us essentially sort of a potato, which is defined here in this volumetric space. And then after training, what you get is a 3D mesh, which approximates a template of your object category or your object type. And then you also have some fused dynamic features here, which are just an augmentation with dimensional shape, where we attach to each 3D point a set of feature vectors that are the corresponding dynamic features. The way this is what we do those, that's because these features are unsupervised, but at the same time, they tend to be sensitive to different object parts. So you see here again the DCA-based visualization that different colors tend to pop up from different parts of the object. So here you see this even better. So I have a bunch of training images here, the corresponding dynamic features there. And you see that the dynamic features tend to light up or find correspondence automatically for you. So this is essentially decomposing your dynamic objects for you without having to provide any manual supervision. Then we take an input image like that. We have our base shape here, which is a template for that image. We have a de-renderer that tries to capture different factors that explain how this template fits the content of that image. Then this goes into this rendering function that produces back the RGB pixels, the mask, as well as the dynamic features that then we match to the dynamic feature that actually measure in the image. So it could be data features from the input image, they have data features in the 3D model, and then we try to match them just in the same way as we are matching pixels. And this is very similar to what I showed before when we were doing neural feature fusion. And so then I'll set up some tiny boxes you train. And this is fine, but this is only for a single function category. But as I said, we really want to expand this and do dozens, if not hundreds of different categories. I'm not going to be fully general here. I'm still going to stick to quadrupeds essentially, but I will try to remove the restriction that you have to work on your horses, cows, etc. So we want a model that's able to do all of them in one go, which is actually quite hard. So the way we do this is by tasking our encoder with coming up with the same files as before. But in addition to that, we also produce with the encoder here a key vector that then looks up in a sort of dictionary of base shapes that we are learning automatically, a corresponding small set of possible matches in this base sort of basis state, like maps with weights for those, and then when you can recombine those canonical shapes, if you like, into a shape that is the base model for this particular image. So essentially on the fly, you try to construct a template for what the object category would look like here based on that image by recombining sort of fixed templates that we are also learning, fixed in the sense that they're always the same for all the images. But of course, they change over time while you train it because we don't have time issue. So you can combine them, you get some proto template for that, and then you get your deformation, articulation, etc. that try to map that particular template to what you actually see in the image, and tries to match them with appearance, pattern features, and the shape. So these are an example of the results you can get. So this is 3D font on the web, again, poster on Thursday morning. And this essentially works for about 100, actually more, categories of this meta category, which is quadrupeds. And this is actually quite nice because you can capture shapes which are very, very diverse and still works robustly. And here you see some examples of this running in practice. So you see the input image on the left, then it's actually shaped and rotate around. You see that there's also a skeleton that helps to explain the manipulation. And then because you have that, you can animate those shapes. These are not just single image reconstructions, but it's a map that takes your image into an instance of object category. So now you have the dynamic category, which you can animate and articulate. Okay. So this is another example. It works also for non-real objects like this cow here, which is just its model. Just because the model actually relies quite well. And you can get some crazy shapes too, and it still works. And if you want, you can apply that on a frame-by-frame basis, and it works. So the reconstruction looks there pretty smooth. But again, it is not dynamic constraints that this would actually be over time. This is simply a symptom of the model being quite stable, working quite well. Okay, so that's one thing you can do in terms of trying to automatically decompose, in this case, object categories, is sort of consider parts which are dynamic, and you can use the parts to try to explain motion, right? But what if you want to go beyond that? So this is actually a question that I've been asking myself for a while, and it's a tricky one, I think. So what is a universal model of dynamics, right? So we have seen before that you can have something like SMTL, which is uncrafted. Maybe you can have something like extension layer built, which is less uncrafted. It's still the topology of the skeleton, the articulation is still fixed, but the actual shape and possible articulations are completely learned. So this is less constrained than something like XMPL, which is really carefully crafted by hand and with a lot of expert vision. But still, it's just quadrupeds. What if you want models like a model that is able to understand a human, a horse, but also a piece of paper, a towel, a door, or a cabinet? So all these things are things that have certain motions. So how are we going to come up with a model that can explain those? So one possible way to try to look at this problem is to work with a black box. So you train a model that you think is understanding motion, and now what you want to do is to have a way of probing it with anything else. And one way to do that is to do that through a dragging interface. So here we have an image of sort of chest, which has a handle. We draw a drag, and we want our model to be able to predict what's going to be the effect of dragging that part physically, right? So there's no physics here. It's just an image of pixels, and then the drag is just an RGB. But what we're trying to get the model to simulate and understand for us is what will be the effect of that motion in reality. And this is, if you think about it, it's completely genetic, because you can have a chest, but you can also have a laptop, and it should work just the same. You don't need to specify any skeleton, right? It's completely open-ended. Of course, this is very ambiguous, so you start from an image I naught and driving that to new. And what you want to do is to sample an image that is a possible response to that particular drive. But the idea is that the interaction happens at the part level, not at the global level. So you're not translating that object, you're only translating, in a sense, the smallest possible part still makes sense, physically, right? So the way we did that was still quite basic. So we went out there, collected a set of training objects that are synthetic, which have articulations of different kinds. And we have randomized that and extracted this set of pairs where you have a starting image, end image, and then we label those with arrows which correspond to these drugs. We have a whole bunch of those, hundreds of thousands, and from that we can train a model that is able to do prediction. So the model, not surprisingly, is just a diffusion model. I don't want to go into the details too much. Suffice to say that you start from the conditioning, which is the starting image, your drug. We have a certain way of encoding the drug that I encourage you to look at in the paper if you're interested. Then you start to denoise an image of what the chest will actually look like once you apply that drug to it. And you can have any number of drugs from 0 to n. Okay, so it's quite flexible. And here you see some results. So these are on segmented real images. So you can open the way open here. You can close the doors of that cabinet, close the laptop, so close this lid. Again, this handle. You can do one or more doors, and the model starts to understand what you mean, etc., etc. Works on glasses, so you can bend the stick of the glass, etc. And more and more results. And because we start from a chain model, actually stable diffusion, then this actually is, even though the training data is actually quite simple, it's just synthetic data with some randomization, it still generalizes okay to real images. But this is not really yet. We are thinking about how we can extend this to 3D as well, of course. But it's just to give you a glimpse of what's going to happen in the future. Again, this is completely open-ended interface in which you don't need to have a specified topology for your object. You just want to get a sort of open-ended understanding of what it means for object to articulate a model of their dynamic, which is ideally fully universal, fully open-ended. Next, I'm going to make the points that a lot of compositionality that we can get into the geometry might come just from the usage of language, right? So in particular, we can consider the problem of textability, which I think is quite interesting. So here, for instance, you could say inviting acts, and the goal would be to sample a model n from this pseudo distribution that condition on the textual prompt gives you a density over the possible to the object might correspond to this concept. Okay. And if you think about it, language has obviously compositional properties, and the question is, if you train a model that goes from textual prompt to an object, can you benefit from those compositional properties or not? So one thing we found that is quite interesting, again, this is also a poster here at CVPR, is language control 3D editing. So what you can do here is you can take objects, in this case we're using, I'm going to explain why in a second, a particular encoding for those objects is called Shapey, which is a technique by OpenAI. Okay. Then we can specify with a textual prompt not what we want the object to be, but how we want the object to change. So it could be some global edit, like for example, make it look like rainbow, so change the entire colors so that it looks different. But it could also be a local edit, for example, add a little hat to it, or add a sweater to it. So because the model is based on language, it can potentially understand some level of composition and apply that to your edits. So how does this work? So the thing we wanted to do with this paper was to study the problem of learning interesting latent spaces for real 3D objects. And because we did this in university, we didn't think we could train this from scratch, so we used what the table to ask, which was Shapey. Again, this is a latent space for 3D objects that was provided by OpenAI, where it's trained using the quality technique. So what the idea here is that starting with the object like that, there's a network that maps that to a latent vector. Okay? And then there's another network, the decoder that takes a latent vector, gives back your object. In this case, this is actually wrong. It should be the same as before because we didn't apply the edit yet. Sorry, this is a new slide. Okay, but what we wanted to do was to actually change this latent encoder into some adding to it this editing capabilities. So the way we do that is by take the object, we extract the latent space, which is the vector, and then we learn a box here, which is called shape editor, shape E. that takes as input, if you like, the instruction, the way you want to actually change the object. Then finds out different latent vector here, and that text gets decoded in the object you actually want, which is the object that we have here as input but changed. And the way we do that is by training this using an existing off-the-shelf editor for 2D images. So we're essentially distilling the editor into a 2D latent editor. So again, we have the object, we extract the source latent, then we apply our shapey editor to get the edited latent. We decode that, so we get corresponding to the reconstruction for without and with the edit. We render that, so now we have images. And yeah, this is an image of the recording with a hat. And then here we use the SDS loss. And the SDS loss is trying to make your editor change the input image in such a way that the edited image looks like it's compatible with the prior on edit, which is captured by a given image level editor. So here we use two variants of that, an image to image editor that takes an instruction, and that takes an instruction and applies that to the image, or we just use stable diffusion as a surrogate for the editor. With the SDS loss, we can then distill everything back into what? Not on editing a specific object, but in learning the weights that go into this network that then is able to apply this edit directly into this space. We also make a little distinction between what are global edits, like change the style of the object, and local edits, editing the parts. We have a way of automatically figuring out the tension map, which is to say which is the part of the object that the edit is meant to change, and then focusing our efforts in only change that part versus the rest of the geometry. Okay. So why do we want to do this? Why latent editing? Well, I'm going to come to this point again in a few minutes, but one thing we can get immediately is that while this latent editor doesn't work for all counts, so you still have to train for one count at a time with a few counts. Okay, so that's we lose a bit in generality. The point is that once you have trained this latent editor, it's super fast. So normally, if you were to use SDS loss to try to edit the object, it might take something like 30 minutes. But once you are able to do that latent space, it takes 1 second. So if you want to edit a whole family of objects, so you have, I don't know, all the Schmerz, so you want to change the color of their hands. So their hands are good, then you don't need to pay the cost of 30 minutes by hundreds, but you only need to do that once, and then you can edit all your objects in very, very quickly by using the editing capabilities you have now acquired in latent space. So the editing latent space is in fact much simpler than editing the 3D model directly. Okay. And this is a pretty complicated table, but the message here is that you can get better quality results by editing all the objects together in this fashion, and eventually it's actually much faster than trying to edit one object at a time. See here's an example of global editing. So changing the overall style of your object, make it look cyberpunk a little bit, make it look like Lego. And then local editing is probably more relevant to this workshop. Add a hat, add a sweater, add a little crown here, and add a snowboard. Now the quality is limited by the fact that we're using this latent space, which is shapy. So that is how good these objects are for that model. But nevertheless, it's interesting that we can learn very, very effectively sort of latent actions that apply universally to all these kinds of objects. And in fact, the latent space structure is also quite interesting. So what you can do is you can take two objects here, like the Caesar, that are being edited by changing its color, subtract the Caesar without that edit. We're doing this literally as a subtraction vector space because we have expected codes, so you can achieve the algebra there. Then sum the code for the shoe, and off you get the code that represents the shoe with that effect applied. It seems that this level of editing, this little algebra actually works because certain space is decoupled, which is actually quite interesting. The same is true here for the class. So you can see that you can understand how the latent action works in space, but single subtraction, once you have that delta vector, you can apply to different objects, and that the same style is going to be applied to the other object. Okay, I think I only have 5 minutes left, so very, very quickly. We'd like to conclude this by insisting once again on this sort of idea that language can help you to learn positional structure when it comes to generating objects. The standard approach here would be you take an input, you have a multi-view generator that produces a set of objects, which set of views of the object, which are corresponding to that input to be text or an image. Then you can have an entry here that does the construction and spits out the object there. Okay, that's the model we're going to use. what we asked ourselves is, what would we take to take this and make this 3D generation start of sufficient quality so that people in the gaming industry, for example, would actually want to use the objects which are produced by static 3D generators. There are a bunch of factors that are very important, but the ones that I think are maybe relevant to this workshop are two. This control in terms of prompt fidelity and also material control. So by material control, what I mean is that you want to be able to specify your prompt what your object is made of. So here we say, for example, a book made of metal. So what you want to do is to produce it, to reshape your object, but also want to produce the albedo, that would be the unshaded color. You want to have the roughness, and you want to have the impedance, which are two physically based properties that describe how the DRDF, the direction of the distribution function, works for its object, and these capture the property of the material. So how shiny it is and how metal-like it looks like. Okay. So we did that, and we trained a model that is able to understand these factors and map them from language to the 3D construction you have. And these are some examples of the results we get. Okay. So this is called Meta 3D Gen, and is the latest, greatest from our group in Meta. So this is basically the result of a year and a half of work, I think. So now it works quite well. So you can specify fairly detailed descriptions in language, and you can get this very nicely looking high quality object that correspond to the controls, both in terms of the shape and the attributes of the texture as well as the materials. Now, what I want to make the point here is this level of complexity that we can get by having a powerful image generator combined with a power language model, and then eventually mapping everything to 3D. So here's, for example, the prompt is a stylish metal statue of a llama with a fancy genuine logo engraved on one side and May 24th engraved on the other side. See here 3 different methods, HTTP3 and Lumageni are two commercial competitors, and it's ours here. And let me show you this again to you. So the end of the video, sorry about that. See, genuine is one side, May 24 is the other side. Again, an example of composition through language. And this is okay, it doesn't work all the times, but when it does, you're quite happy. It's actually amazing that he would do that at all, to tell you the truth. Okay. But this is generally speaking, the model we got is very good at following instructions. So here we have a rabbit character with a straw hat and superhero costume. And if you look carefully at what you get from different methods, ours is essentially the only one which really follows the instruction very, very carefully. So it's a straw hat, has a superhero costume. The other ones will have some mistake in that. Okay. And here's again a composition where you have a more fortunate hammer on an anvil. And you can see here that our method is able to get all the elements correctly and also get quite a nice shape as a result. So to conclude, again, there are 3 papers that hopefully are going to come out by the end of this week or very early next week. If you're interested, please have a look. There is one on the actual generation from text, another one on text generation, using text, and then there's a meta paper, a sense of paper that summarizes the 2 and combines them together to get these typical results in terms of text generation. Then just thanking the team in Oxford, a lot of people there, a lot of people in Meta. Many of these people had a contributed to the work section today, but of course we couldn't speak about everything. And then just to summarize what I talked to you about. So one was using 3D to lift 3D information into some coherent 3D space. You get some benefit from that, including having structure in 3D construction in the first place, maybe language, yeah. Part dragging, so this idea of developing this sort of universal motion models. I show you the learning motion models for actually quadrupeds, and then I wanted to try to generalize this beyond that. Part dragging to be an interface to probably sort of universal motion models, so that is quite interesting. Part editing and data space, so developing this data space structure for the objects which have this property where that sort of exposing sort of almost like linear fashion, the structure of the parts or the properties of the object, quite useful for understanding the structure of the 3D there. Then, of course, a lot of composition comes from language. You train simply, so to speak, text to 3D model, then you get some compositionality for free just because compositionality is there in language in the first place. Okay, thank you. And sorry for being 1 minute.
Wondering. So, you thought about like what it future.
Yeah, it's an interesting question. But I mean, it's a very open-ended question also, I think. Do you have a more specific question or just completely open-ended?
Yeah, so kind of people now working on like, I mean, changing from nerve to speed reduction,
Yeah.
using diffusion, and
Well,
there are a lot of work there, but I mean, what will be the future, like extend object to scene or?
okay, so I mean, I can try to make some very high-level predictions here. So first of all, I think the next step is 4D. So today, especially when it comes to do also image understanding, it's more useful when you want to explain videos. But videos are interesting, especially when there's stuff which is moving inside the camera. And this is where, you know, the models are still not very good at. So I think that's definitely something we want to do better in the future, and I think it's going to come very soon. So 4D, right? In terms of the sort of technology we're going to use, so is that going to be diffusion? Probably for a while longer, but I don't think that's fundamental. Or using neural forget slotting, probably that is also not fundamental. And by the way, these things, they tend to be more interchangeable than you think. So if you implement neural very efficiently, can almost get, not quite, but close to the efficiency of batch slotting, at least in terms of how much memory it takes, for example, to train. So these things are not so fundamental, I think. What is another interesting question to me is, what does it mean to have a clear representation? So now we use primitives like points, diagonals, triangles, vertices, blah, 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 right? This is going to be very more important for applications, for example, gaming or special effects, because this is what software for professional and, you know, any computer graphics software stacks actually use. That's the language of computer graphics today. But project that in 10 years in the future, maybe the way we're going to do computer graphics is going to be completely different. And the idea of representing something with a triangle mesh is going to be completely obsolete, right? So a lot of the stuff they're doing is trying to take machine learning and get it to produce outputs in the space of representations which are good for computer graphics, because that's what we know, and that's what the tools we have, like PlayStation, actually does use understand, right? But project that 10 years in the future, that might actually go away. And maybe what we need is complete just neural network pipelines where geometry is largely implicit or entirely implicit. So I think that's the really interesting question. Is that going to happen? Maybe.
Thank you.
Well,
Let's thank everyone. Thanks. Now, my pleasure to introduce Professor Katerina. Yeah, exactly. Katerina is an associate professor in the Semantic department at Carnegie Mellon University. Research lies in building machines that can understand the stories portrayed in videos and conversely using videos to teach machines about the world. The goal is to work in building machines that comprehend movie plots, while the ultimate goal is to develop a machine that would prefer watching a film over action. Prior to joining TMU, he spent 3 years as a postdoc at UC Berkeley with Generative, and also at Google. And she will talk today about memory prompting and direct feedback for 3D see understand. This is only to work on.
Do you know what I need to press so that there's no mirror? I think it's from here something.
Okay, here.
Okay.
And then
Yes, thank you so much to the organizers for organizing the workshop again this year, the second time. Thank you very much for inviting me and giving me the opportunity to present our recent work from our group. The topic, the word of compositionality is already very complex and means different things to different people. A very simple maybe explanation would be I give you a new picture and I can of course give you a label center. You don't understand what this means, but you go and check the definition. Definition is with respect to things that you already know. So I would say compositionality is how we compose things, we already know to build new concepts and to quickly understand new concepts as opposed to having training get out that new concept directly. So this talk will explore three types which can give us compositionality. The first one is through memory indexing. We'll discuss some memory augmented neural networks that along with a parametric component, there is a big non-parametric external component where your memories are there, they're retrieved and composed. The second is through generative feedback. How can we use rendering to and compositionality to lift monocular videos of multi-object scenes into 4D. And the last is compositionality in 3D through unification of 2D image parsing and 3D scene parsing. Okay. So compositionality through memory indexing. So this is a work that I really like, despite the fact that it hasn't really let's say picked up because it's only applied to PartNet. It has very good results on PartNet, as I'm going to show. So we'll build neural networks that, along with the standard parametric component, there is another component we call the retriever that has access to a memory, to a set of memories. Every memory, you can think of it as being a labeled point cloud, okay? Completely point cloud listing, where the parts are labeled, okay? As you see, different colors are different labels. And we'll be parsing new point cloud input by essentially retrieving from those memories, okay? Here's the retriever. We are going to featureize each one. We're going to do k-nearest neighbors, bring the ones that are most similar along with their party compositions, and then we'll feed those memories to a modulator, a standard, attention-based transformer that instead of just processing the current input, also processes the memories. So you try to understand essentially the current scene by relating it to the memories, to the things that you've seen before. And then you label the output, and every labeled part of the memory is featureized and is mapped to a query vector. So this architecture should remind you a little bit of the standard detection transformers, where we have a bunch of slot vectors or query vectors, right? So they're shared across scenes, and these featureize along with the scene, and eventually they segment the object. So the same thing happens here, but instead of just having those query vectors that are shared across scenes, these standard detection transformers, you also have query vectors that have identities. So this query vector is the back of the chair that you saw yesterday in your office. All right. So we allow those memory query vectors to also participate in the scene parsing and claim parts. I'm not connected into Zoom. I see. Do I really connect?
Yeah, because some people are joining, it's on the calendar invite.
I see. Okay.
Sorry.
Okay.
Sorry for that. No, I think. Yeah. Sorry.
Just give me a second. So it should work now, right? Okay. So basically, along with those queries that are scene agnostic, we have those, identifiable queries that are memory part vectors. So when that memory part vector is used to capture one part of the current scene, then the benefit is that this segmented part is automatically put into correspondence. So this part is like similar to the part that actually claimed it. So you don't need semantic labels anymore. You don't need really, the space is not anymore a language space, is the space of your memories and their decompositions. And so what this allows you is to do is, instead of having one language label, which is the back of the chair, you can have as many labels as back of chairs that you've seen. Okay, so you can recognize your grandmother's back of chair and so on. And this also explains how, let's say, Eskimos know more about snow than us because they don't use the language space of the snow, they use the types of snow that they've seen, and they see much more snow than the average, let's say, American or Western civilization people. So basically, memory provides the label space to parsing things. That's the idea of these networks. And again, this should remind us of those segmentation transformers that you have in the image and have these colorful slot vectors that can explain the scene. But our slot vectors now come from memory. Now, along with those memory slot vectors, you do have those gray guys there because new things can show up in the scene that are not part of your memory, and you still want to segment and recognize those. So we call those networks analogy forming networks because they form analogies to things that you've seen in the network. We also call them analogical networks, but unfortunately this term is not as good because like the digital versus analogical is a little overloaded. So the way we're going to treat those networks is through, within scene augmentation, we'll train a labeled point cloud and deform it in two different ways. And we will use one deformation as the memory to parse the other deformation. And the good thing with this self-supervised way of training the network is you have this labeled point cloud, and when you deform it, you know exactly which part should claim each part. So you can put very strong losses that tell each part of memory which part of the input scene it should claim. And as you see, the blue should claim the blue, and the green part, and the red the bottom. So you train this segmentation transforms in this way. And again, here we don't use absolutely any semantic labels, so nobody knows that the blue is the top of, let's say, the lamp. And here is how we do our cross-scene training, where again we don't use any semantic labels. We have access to this set of memories, and we retrieve, where retriever tells us what to retrieve, and then we minimize essentially a segmentation loss. So we only train the network to segment, but not to label. But you'll see that the label is going to emerge automatically through similarity because the most relevant memories are retrieved and are used to label the input in that memory part label space. Now, the good thing with this memory prompted, the transformers, is that depending on the memory you retrieve, you have different granularity of the resulting labeling. So the same input can be labeled differently depending on which memory you retrieve, with less coarser part granularity or finer part granularity. So our baselines are the standard detection, 3D detection transformer. We have a point cloud and a set of scene agnostic queries, as well as a task segmenting here for partner that tells you how fine or coarse grain you want the segmentation to be. And another very interesting baseline is a standard memory augmented detection transformer that has access to memory, much like the analogy forming network, okay? But so it attends to those part embeddings, but doesn't use them as query to segment. So only those agnostic queries are going to segment the scene, but you're still allowed to retrieve and attend to things from memory. And I mean, needless to say that all this line of work is very inspired by retrieval augmented generation, right? Used in large language models, okay? We've seen language models doing much better when they have external homogeneous repositories of facts and so on. So this is very much inspired by that. The downside of this model is that unfortunately you cannot get zero-shot labeling. You can segment, but it doesn't put things into correspondence because you don't have those nice identifiable queries to use. You just attend to them, but you cannot use them to segment. So in PartNet, if we compare our model to the baselines, you see that when many examples are shown from a category, all models do well. But when you have one shot or few shots, the memory augmented models, which is analogy forming network and retrieval augmented jitter, do way better. The reason is that from external memories allow fast learning. Whatever you see, you just directly update your memory. While parametric models need gradient-based learning, and this is slow learning. You need many gradient steps for the ways to update to explain a new category, and also you want these gradient steps to be decorrelated and so on. So we want to combine here fast learning with memories with slow learning of gradient descent over weights. Yeah, so detection, the standard parametric transformers that everybody is using is this orange bar. And as you see, if you fine-tune it, it does well, but still not as good as the memory augmented neural architectures. Yeah, so now we, at the same time, we also have a label propagation without using any semantic labels, simply because our analogical networks form explicit correspondences to parts in memory. You can also transfer the semantics of those labels in memory to the parsing of the current point cloud. So basically, you never train the weights of your network knowing semantic labels, but simply because you correspond to memory, you just inherit the semantic label of the part. So here is how this looks like. You have an input, the memory, and here the corresponding output. And the most interesting result is when we keep to the network different classes. So we asked it to segment the TV by retrieving a clock. So you see what the network did? It said, you know, this part is not present. I think this red part is something similar to this, and this red part is similar to that, and this also in the new part. So this is also segmented by this scene agnostic queries. So you see some sort of spatial abstraction to arise simply by using this memory augmented learning. So we're very, inspired by this Mosh Bar, who said that the way we understand the world is through analogies to things that we have seen. And if the situation is complex, you need to do multiple analogies. So don't ask what it is, which is the language guided learning tells us, but more ask what it is like. So the takeaway is we can compose concepts by retrieving memories, and we can adapt fast to new examples. And we don't need to build different models for few shot learning and many shot learning, like you see many papers nowadays, they say few shot on the title and so on. This memory augmented architectures work the same way for many shot and few shot. And this makes sense because, when we see a new example, we're not supposed to know whether this is a few shot or not few shot example. So these memory augmented architectures do this for you under the hood. Yes. So the next thing I want to discuss is compositionality through the generative feedback. And specifically, we want to move from static 3D point clouds to dynamic scenes. And those dynamic scenes will be in the form of monocular videos. And the way we're asking is, can we use today's generative models and compositionality to lift monocular videos of multi-object scenes into 4D? So we've already seen 2023, I think was for sure a year of open world 2D to 3D lifting. Right now we can lift in 3D any image using reprojection error on the view that we see, as well as diffusion priors, diffusion of losses. You render your differentiable 3D representation to views that you do not see, and you evaluate how likely is that render for my diffusion model, and this gives you additional losses that allow you to do this in the wild 2D to 3D lifting, right? And the first paper, of course, that did that is best paper award in ICLR 23, Drake Fusion, okay, that used the generic image diffusion model for this, score distillation objective. And since then, people have come up with a beautiful, much more focused objectives. And here specifically, we're using 0 to 3D, where you condition the diffusion model with the view that you see to predict how alternative viewpoints will look like. And this is what supplies the score distillation losses. Now, unfortunately, all those 2D to 3D lifting results are all concerning a single object. Okay, which is indeed is not surprising. It's much easier to predict how a single object will look like from different viewpoints than to predict how a whole scene will look from different viewpoints. So the question we're asking, can we use those object-centric generative priors to lift whole scenes into 3D instead of a single object? And here is our work that appeared on arXiv very recently. It's called Dream Scene 4D, where we take monocular videos like the ones you see on the top to generate 4D, 3D over time, outputs. And the interesting part is that we don't do per frame lifting, but rather those outputs are all connected. So what we're using is 3D trajectories, okay, that connect essentially those 3D points over time that are rendered. Again, the very similar idea, they're rendered, and we use reprojection, pixel reprojection, as well as motion reprojection from the view that we see in the monocular video, and we use score distillation losses for the views that we do not see. And because score distillation losses are object-centric, what we do is we decompose the video to apply the object's entry losses, and then we recompose it to make sure all objects are in the right place and the right depth so that reprojection errors are minimized. So essentially the methodology of this approach during C4D is first it decomposes a video into different objects. As you see here, we use segment anything plus temporal linking. And then we focus on each detected object and we use score distillation losses at every frame, as well as reprojecting RGB values and motion. The motion of every object is explained through a set of 3D Gaussian trajectories. So we have triplane features that are test time essentially trained to predict displacements, dx divided v, for every point at every frame. This is very much the same representation used in Dream Gaussian 4D, ICLR 2024. And then we take all those objects and all those essentially 3D object droplets and put them together and do reprojection errors so that we place them in the right place. Okay, so I'm showing in this slide the original video, and we show our reconstructions from the same view as well from alternative viewpoints. Okay, and the important thing is that not only we see the rendered RGB, but also you can look and evaluate the point trajectories, and this is what we did. Now you may say, why would you care about this? Why would you go and get monocular videos and lift them into 3D trajectories? Well, this is extremely important for visual imitation. So if you want to teach robots how to do tasks and so on, right now you need to use kinesthetic teaching. You need to move the arms of the robot, or you need to use a teleoperation or other expensive, let's say, instrumentation. And if we're able to indeed do fine-grained video perception, as shown here accurately, then we can infer how the world changes as the human manipulates the scene, and then ask the robot to carry out a very similar manipulation. In this way, we can have very dense in time reward functions for our robots for reinforcement learning in the real robot platform as opposed to in simulation, right? So modeling, fine-grained modeling of the video scene is extremely important for, of course, activity recognition and robot imitation. And here is some results that we show under heavy occlusions. We compare here with co-tracker, which is a method we really like. We were very inspired a couple of years ago for the task of tracking any pixel in a video. So, my student Adam Harley published a paper called Independent Particles, PIPS, and then co-tracker, address co-tracker, essentially pushes this to the limit, extends this by tracking not independent particles, but rather multiple particles at the same time. And here I'm showing the co-tracker results. We want to see, can we track pixels even better? And one big question we have is, for the task of pixel tracking in videos, can we solve it in a feed-forward way with big transformers trained on insane amount of supervised data? Or actually, we need to follow an inverse graphic approach, which is try to imagine the 3D scene behind the video and how the 3D scene would move, put as much priors as you can, and render, and would that inverse graphics approach does better pixel tracking. So this is where this work is trying to go, essentially. I mean, we're not all quite there. I mean, we are doing, as I showed, under heavy occlusions. Of course, we do much better than the feed-forward approaches, but there's still a long way to go. Here, I'm just showing that, yes, our people prefer Dream Gaussian 4D, Dream Scene 4D over, previous methods for scene lifting, simply because there's no other previous method that can lift the whole scene. There are object-centric design for objects, and once you're applying the whole scene, things break. And here, without any training, this is a training-free approach. This is like a test time optimization approach. You are able to do very good tracking over, co-tracker and PIPS plus other point tracking methods. And the last work I want to discuss is compositionality through 2D and 3D unification. So far, one thing that is true and that actually bothers us is that 2D and 3D vision are kept separate, and they're also being investigated in different workshops from different communities with different model architectures. And we're trying to understand, actually, I really like the question, where this is going. Where is 3D vision actually trying to go here? I mean, clearly, augmented reality and, gaming and so on is one direction. So yes, for graphics, it makes a lot of sense. But what about for people that care about perception, better understanding of images and videos? How is 3D about helping in that way? Okay, so this is that's also what the previous method was trying to do. Use 3D as a way to get better video understanding, okay? More fine-grained video understanding. So one thing that we saw is while foundational models, 2D foundational models are taking over the world, in Scanet, the state of the art was still not a foundation model. It was mass 3D trained only on Scanet and evaluated on Scanet. And then what we found is the following, is that Scanet benchmarks actually use specific benchmark provided mesh sample point clouds as opposed to directly capture sensor point clouds where you just have images with the depth and camera pose annotated that are obtained through some certain post-processing. And because of the tiny post-processing, the mesh point clouds are slightly misaligned with the input images. So an approach that instead of trying to directly operate over those point clouds, instead operates over the images that actually give birth to the point cloud at the end of the day, will suffer from that misalignment. Okay? So we believe that this is potentially one reason why 2D and 3D communities are kept, let's say, separate. So we said, you know what? 3D data is not as scarce that people want to say all the time that we hear this standard quote, 2D is everywhere and 3D is so scarce and it's so scarce. I mean, it depends what you mean with 3D. If 3D is just images with camera poses, I mean, they're not that difficult, just find some slam, nothing can be moving. So that's the other problem with 3D vision, that, the scene cannot be dynamic. But, then you get slam, you get the depth, you get the pose, and we can get a lot of this. So in this conference, we have this model called ODIN, omnidimensional instance segmentation, that can parse both 2D images and 3D data. And the 3D data here, I mean RGBD images with camera pose. That's exactly what I mean. So the way you think that is the following. So here's the following realizations. 2D and 3D for visual recognition, and not for graphics, just to be clear here, only differ with respect to the positional encodings of the tokens. By tokens, I mean the patch features. So in 3D, the positional encodings capture XYZ coordinates, while in 2D, the positional encodings capture pixel coordinates because we don't have camera pose, we don't have depth. And we can totally interleave 2D layers, attentions that use 2D positional encodings with 3D attentions that use XYZ positional encodings, and benefit from using those 2D layers because 2D layers will have been pre-trained on an insane amount of 2D images labeled with language. So this is what ODIN does. So this is how it processes the standard image, the standard 2D backbone with a mask decoder, much like the state-of-the-art COCO segmentation models. And then once RGBD images come in, the only thing that changes is that there is a lifting to 3D projection and fusion and projection. So the projection essentially takes the 2D tokens and uses the people camera equation and camera extrinsics to lift them into their XYZ coordinates. That's all that projection happens. There's no parameters there, and it's a differential operation. Okay. Now, once you go to 3D, then there is going to be a 3D fusion, which is the 3D attention. And the 3D attention, because there are too many 3D tokens, if you aggregate across the whole scene, we use K&N relative attentions, K&N transformer, which means we don't compare every 3D token to all the others, but only to the 3D tokens in a radius around the token, in the vicinity, okay, in the local neighborhood. And the important thing is we use relative attentions, meaning that the affinity between two tokens only depends on the relative arrangement, as opposed to the absolute XYZ coordinates, because absolute XYZ coordinates are extremely arbitrary. You can put the center of the coordinate system anywhere you like in the scene, and by changing the center of the coordinate system, you'll change the results of the absolute attentions. That's why you need to be using relative attentions. Okay. And then once you're in 3D now, and you've used things in 3D, you're going to go and project. So this is the red layer. Again, there's no parameters there, but it is differentiable, so that's why you can backpropagate through all these layers. And the projection essentially takes 3 tokens and projects them back to their corresponding 2D image locations. So this is what ODIN does. It alternates between 2D projection, 3D fusion, projection, 2D fusion, projection, and so on. And the 2D layers are shared between images and data, and the mask decoder is also shared, so the shared weights everywhere. So this sharing of weights helps dramatically for performance. So now, because Scannet labels and evaluates those match point clouds, and because Odin uses those sensor point clouds, we're going to transfer the features there and predict the labels and evaluate and backpropagate. So the results look as follows. We are not able to beat Mask 3D in Scannet. Scannet has 20 label classes. We came very close, but we were not able to beat it. Now, at the same time, Mask 3D is evaluated on the sensor point cloud, which is where the one that we're using, it does much worse. Now, once you go to, semantic segmentation, we're doing also better. Now, as you go to Scannet 200, things change. Because in 200, there are 200 categories, and many of them are long tail, like they show up very early in the Scannet 200 training data. And there is exactly where Odin wins, because it uses the super powerful, let's say, clip 2D features. It starts from very, very important initialization. So you'll see that for semantic segmentation, for instance segmentation, it does okay in the common classes, but does much better in the so-so common classes and on the tail classes. Okay, so anything that is not super common on the benchmark, Odin does better thanks to 2D pre-training. Also, Odin, because it operates directly from the sensor point cloud, you can use it as a perception, let's say brain of an embodied agent. And here we have a helper. This is our model for Alfred benchmark, or the Teach benchmark is the state of the art, and we're able to improve the performance of our model simply by swiping the Odin, detection, as opposed to just 2D detection and then post-linking. Now, having said that, there are multiple works here, OpenScene, Concept Fusion, Panoptic Lifting, and LF, that also try to use 2D foundational features on 3DCs, much like Odin, but they do this in a zero-shot manner without being able to train, this fusion. And of course, Odin, because it's also not zero-shot, right? It can use 3D data. It does better than those methods, as we show in the paper. So the takeaways is that labeling and evaluation protocols from 3D vision benchmarks encourage right now 2D and 3D divide because of this mesh point clouds that we just said. But we do believe that 3D vision should be evaluated and trained in the wild, okay, for embodied agents, robots that move around, and so on. 2D and 3D can be unified in terms of positional encodings, that as we said, that Odin is one concrete architecture towards this unification, and of course, much more should happen in that direction, okay? So the last thing, and I think I need to close, correct? How many, do I have any minutes or? One minute? Okay, yeah, I just want to say that where is 3D useful? So we had recently this learning from demonstration method, 3D diffuser actor, that combines these scene representations from Odin that I just said, takes 2D features, gives them in 3D, use 3D relative attentions and so on for denoising robot trajectories, and it directly went to the top of the benchmarks. Okay, so I do believe, and this is quite important, because right now everybody in academia and industry does learning from demonstrations. For robots, there is this current robot Canadians of 2024, and 3D scene representations are able to do so well. And it is very important. What is the form of this 3D scene representation? It is tokenized, right? So every patch is a 3D token, and there are attentions in that 3D space, as opposed to collapsing everything into single embedding vectors that essentially you do not permit generalization, because anything that changes in the scene will affect that embedding vector. So the summary of the talk would be: we can segment and track novel scenes with little to no in-domain training using compositionality, rendering, and generative priors. Thank you very much again to the organizers for this workshop and for giving the opportunity to present our work. These are the three papers that I mentioned. And they're all on archive, and the first and the last also have a publicly available code right now. So thank you very much.
Loading work, it showed that there's advantage to putting 2D features lifted into 3D space. You also run an ablation where you remove the 3D part.
Yes, the 3D fusion, right? Yeah, yes, actually, I removed the ablation slide because I didn't have time, but yes, there is this ablation there, and there is a big drop where in the instance segmentation, not in semantic segmentation, if the only thing you care is, I want for this 3D point to label the semantic label, and you don't care to segment it into different instances, there's no drop. This 3D fusion is important only per instance. Yeah, great question. Yes?
So for the results, what I noticed is that the 3D views were reduce some objects in general. So then is the model also able to change the background, for example, as the views change, or is
Very good. Yeah, great. So this scene for the segments and the object and the background static scene. For the background static scene, we use standard SLAM, we use dusted for initialization, and then gradient descent to find the right depth scales and the camera pose. So then you have this nice background scene. And then you have every individual object lifted to 3D and completed with for distillation losses. So the background is also there, yes. And as we move around, we see different parts. And again, there is one part in 3D I didn't mention is there is an inpainting part. So the background images are inpainted because the objects create holes. So to be able to change the camera view and see a complete background, you need to inpaint the background image as well as the image of every object because the objects are often occluded. Yes, and we use standard, not very standard, but we use the latest inpainting models to go from partial view into complete view. Well, thank you.
So I think now we have a voting station, and the voting now we have not for the registration call, but we'll be back here for the talk by midnight at 10:45. So unfortunately, we're not able to make the organizer voting session in this group. Is Thank you. Thank you. My card is I'm saying the expression is normalized spot defined so far that they don't.
Yeah. So that part is based on fitting back speech. That part. But then again, oh, they should be out by so yeah. In some parts like they let's say it's
Yeah, of course, that's what that's. Instead of one, say this is there. You go over there, stand up there, the line. This was.
I love students, but I think still like within the range. Yeah. Within the range of total.
So like this and knock your thoughts.
That's a pretty good one. Yeah, I think it's a good mix of everything. Yes, it's certainly a fun. It's a good story. That's. Social structure. Oh, they talk to each other. Use straight. I don't know if you for folks who are looking for yields and there's a class. This day, I have borrowed some of that. You do that, yeah. But there's things that don't directly transfer because we yeah, different stages. Yeah,
I remember those, one of those string meetings.
yes,
Getting good and then the top of the project. And another one that is visible to some of the lives, I think. I think I managed to borrow two, the reading group and project. But the other one is kind of more complicated, not weekly, but monthly. You could also do it if you're setting up secret. But establishing the routine of because it's kind of you. So it's how to think together as a group. So this can happen. Say, we're not for the other one group, but maybe it's like you said.
So you get a couple of two students, and then I'll be okay. I'm just gonna keep getting. Let's get by students. And I will happy having. So. Yeah, maybe. Yeah, that was a bit stressful. But then I find that it actually helps to have very sequential analysis, because I kind of common thing to sort for them. Otherwise, I have to do it every year. But how that's. Right now, I think you want because now takes care of people with pursue. And then, yeah, but starting in fall, it's yeah, so they're going to start a package, and then we have grants for that. Sometimes senior colleagues, they go actually. That's very convenient. And then every student gets a first year credit, which you can use at any point. So yeah, you have some. It is not. I see. And then roughly 5 years in first year, you basically have to get funding from the senior, but that's also a hesitation. It's not guaranteed, but. I think that's the best. I think as we grow larger, I don't know. What was it? Yeah. It is an example. Has to be, it's not. If you were to think that you use the graphical system. The messages are not the same for that.
So I'm not sure, I think there's a lot myself, but just talking that, consultation.
It's also challenging that if the more GPU computed and maybe storage capacity of your storage. Right, so you give them faster use more memory or storage, they just use all the more. So I thought that I thought it'd be okay. They used to 79. They take care of all that technical. But on the flip side, the basic project between the things like and then I think there was a bunch of so we have to use like a lot of there are downsides to it. We have our own. It should be separate because then we can negotiate better things. Yeah, I suggested it. Oh, we're going to be able to configure it. We kind of figure out the problems to work on that. Yeah. More persons actually said. Yeah, I'm actually going to talk about one page. In the end, we just did a because it's supposed to be on the same time. Be the right show. I think that's what we need to do. Everything's a bit. Yeah. So in this project, my sort of done. I also have other collaborative projects on the same boat that we use their but the problem is once the student you lose access to it, and they have their own it's very different to the university. They have their own managed job scheduling system. So my expertise,
Same experience I had about illegal.
So I've been unsuccessful exploiting that. But if you have any other strategy that we know, because we need more compute to be sure.
Yeah. Yes.
Yeah, it's not like it's easy to get.
I don't want to do that. I'm not sure it doesn't. It's very powerful. You see the yeah. So, I think all the information.
Yeah.
That's because, I mean, so we use Welcome back, everyone. Next we have a talk by Professor Sun, who's an assistant professor of computing at Christ. And he's affiliated to the School of AI and the School of Metaverse. Before joining Christ, he was a research scientist at Adobe Research. He received his PhD from Stanford University under supervision of Professor Lee Davis. His research specialized in vision, graphics, and machine learning with focus on 3D geometry, data generation, processing, and analysis. His academic research include serving as a program community member in CGraph, Asia 22-24, Eurographics 22-24, and Pacific Graphics and AAA as well. Many will talk about learning the functionality of 3D objects. Please join me to welcome.
Thank you for the introductions, Minion. So today I'm going to talk about topic on compositionality in these 3D objects. So before I talk about my research about the compositionality, actually I wanted to clarify what we mean by the compositionality. So we talk about the many things about 3D compositionality, but what we exactly aim for in terms of learning the compositionality. So while I just got this UI, just about the linguistics, I just try to explain, look into some of the literature about the studies of the compositionality in the linguistics and see how people talk about the compositionality in the linguistics. And I found this interesting kind of principle, which is the compositionality principle, states that the meaning of a complex phrase is determined solely by the meaning of the parts and the syntax. So it's kind of like very true that we are seeing this kind of the rules in many kind of the natural languages that we people are basically using the cultures. So what basically this means, so to better understand this kind of meaning, and also this kind of the linguist, the actually should also provide some kind of the counterexample, basically introduce some kind of artificial language, which is does not necessarily obey this kind of law. So what we kind of some counterexamples for this. So let's think about some kind of system. That we are only having some kind of single word, this kind of the vocabulary, and making some kind of sentences, which is actually the comments, by repeating, making things correctly, same purpose. So let's think about this kind of example that we are having the single click, which basically means like select a file, and you basically repeat this twice, and the double click basically means the open the file. And this type of behavior that we create some kind of typically that means deleting the file. So when we have this kind of the language system, then what we can see is that this is obviously kind of the example that the word here, basically the mostly, is not associated with any kind of some semantic meaning, because when you see some kind of the multiple concatenations of this kind of the same token, we are basically getting some very different meanings. So we can see that selecting a file and opening the file does not mean that deleting the file. Right? So this can be some kind of the count example of some kind of language system, which does not basically obey this kind of goal. So while the kind of the triple decrease can be synthetically decomposable into the kind of the decrease, we can see that the mouse click is basically not associated with any kind of the specific meaning. So we see many kind of the language systems we are seeing is basically not this kind of the case. So we can see that many of the language systems are basically is following this kind of principles in terms of that we can basically assign some kind of the specific meanings into each of the words. And the good thing of like this is that we can also generate some kind of the synthesis basically by combining compositing this kind of words. And we can also try to understand some kind of the given the synthesis by having some kind of the understanding meanings of each of the words. And the thing is that we can see this kind of same sort of the rules in many kind of the 3D things as well, especially for the many of the human-made of the objects. For example, here, we can basically identify these objects as a chair because we can see that this object is basically comprised of some kind of components that basically form a chair. We can see that this object is basically having some kind of a backrest, which is supporting your back. And we also have the seat part where we can basically sit on and also having the legs. So when you see that the object is basically having this kind of the multiple components, there are basically some essentially the components to basically form some kind of objects, we can see the meaning of the object itself. So we can also see some kind of same things for the scene as well. So when you see some kind of the office scenes like this, then many of the office scenes will be comprised of some kind of desks and the chairs. So from this kind of some composition of the objects, we can also see some kind of the meanings for each of these three scenes. So we can see some kind of the analogies between some kind of the linguistic 3D vision as well. So then why we need to also work on some kind of composition only in this 3D? So when you basically see that each of the some components for the objects can be associated with each of the meaning, we can basically utilize this kind of information in many kind of applications like robotics, like when you manipulate objects in the same, having this kind of the compositionality can be basically useful because we can easily find some kind of meanings of each of the components. And this kind of the rules also can be used to generate some kind of the new objects or the scenes by making some kind of the new combinations of the parts. So when you also talk about the compositionality in linguistics, there can be two essential components. So one is would be basically the words, basically we also call the lexicon, and some kind of a set of the some kind of the basic components that can basically comprise some kind of the synthesis. And the other thing might be also the composition of the rules. So when you have any kind of the random sequence of the words, they can make some kind of the plot or some kind of the synthesis. Because you can see this kind of interesting. The familiar cases of the like assembly IQ teachers. When you have some kind of the random combinations or random assemblies of the parts, we can get some very weird structures like this. So which means that the rules of the composition is also very important. So we can think about some kind of the important questions in terms of the compositionality in linguistics. The first question might be that how to define words. So there can be some essential building blocks. And based on that, we can also define some kind of the composition of the rules, how we can make some kind of combinations of like these kind of words. And the other thing is that based on this kind of words and the composition rules, how we can also create some kind of the new sentences or new phrase might be some kind of the essential questions in the linguistics. And we can also think about the same questions in the 3D vision as well. So we can also think about how we can define some kind of components for this 3D object or the scenes. And also we can think about how we can define the relationships or some kind of the correlations for the components. And based on the person relationship, how we can make some kind of the new object or the scene. So this might be also kind of the some essential questions in this 3D vision. And also these kind of the three questions can be basically associated with some kind of the these kind of tasks. One would be basically splitting the object into the parts, and the second thing might be basically relating these parts in terms of running their kind of relationship. And the other thing might be basically combining these parts to make some kind of the new objects. So I'm going to talk about these three main topics with some kind of the recent work for this. So I'm going to start with the splitting the operation. So in terms like this splitting, actually, there are some kind of the many questions. And these are basically two main questions that I focused on. The first question is that basically what types of the components are we going to learn? So what kind of the types and also the representations that we use to represent the components of the 3D objects. So for this question, the basic answer might be basically just having some sort of some region representations. So from the very beginning, that we start to see some kind of 3D deep learning techniques like the point net, which was the first neural network processing the point cloud. The easiest way that we can get some kind of the segmentation information was basically allocating each of the points with some kind of the labels. So we could basically learn the point net segmentation. There are different terms like these kind of the region representations for the components for the 3D objects. So if we step further, then we can also consider having this kind of some geometric primitives, since many human-made objects are basically constructed based on some kind of the CAD models, which is represented with the main kind of geometric primitives, like cylinder, sphere, cones, or many kind of things. So when we have this kind of more like parametric representations for each of the components, the good thing is that we can do some kind of the some applications into like editing or manipulating the objects like this. And this kind of the composition also can be learned from the many kind of the CAD the data set. So now we have this kind of the ABC data set or the fusion basically the LOED data set, which is basically helpful to learn this kind of geometric primitives. But this representation may not be suitable for some kind of the many other complex shapes as well. Especially when we see many other types of these complex shapes, it may not be basically possible to precisely basically fit all these kind of the primitives into some parts of the objects. For those kind of the cases, we can also consider basically some fitting some sort of the bounding primitives, which is not precisely fitting to this surface, basically giving some kind of the information about like how these kind of shapes can be some kind of abstract form in terms of seeing some kind of the compositionality structures, define some kind of parts that can be also useful for any kind of some manipulation, the operations. Some very different kind of representations might actually be key points. So when you also basically decompose the shape into some of the some kind of key points, this kind of information can be used to many kinds of some editing or some deformation the applications. And especially for those kind of some key point representation can be useful to for some the sort of the non-rigid shapes or some organ shapes like the human bodies or the animals. So when we have this kind of key points, we can do some kind of the key point based kind of the some information in the editing, and it can be basically useful in any applications. And speaking to the representations for the components, actually one kind of the key idea that I was wanting to introduce here was that they have some functional representations. So this might be was kind of example that we are having some more degenerative representations that can basically represent many things, not only the parts and the key points or the many other things. So here the basic idea is that now we are seeing each of these 3D shapes. It's not as kind of the data, but it's kind of some sort of the domain that we can define some kind of the functions over here. So for example, the key point can be the case that we are having some sort of the, sort of the Dirac delta function over the surface, then one point only has to be 1 and the other point has to be 0. And also the many of the parts can be represented as some kind of some one-up vector, right? Basically having some like binary representations, the values over the surface. So in terms of that, like having this kind of the function representation can be more like general representation that can represent many other things. And we can consider also basically having a, learning some sort of the dictionary of this kind of the functions in terms of like decomposing the given shape into the multiple different parts. So this can be another way to represent this kind of the components. The other big question is that where we gonna basically obtain to learn this supervision to learn those kind of things. So we can consider having some more the explicit supervision or some kind of some indirect supervision to learn those kind of things. So it is kind of the way to learn those kind of things by having some more explicit denotations. So from the the beginning of like 3D vision kind of the research, we started to see many kind of the data set, including the shape net or the part net, which is providing with kind of some sort of the region-based denotations for the person. And also in this workshop, we are seeing also this kind of the new the data set, this 3D comparative plus the data set, which is providing lots of kind of the rich annotations for the parts for many kind of the 3D models. But the challenges in terms of utilizing this kind of more explicit annotations might be that it's hard to scale up because the annotation of these 3D models is much more like a costly than the annotating some kind of images. So the other way that we can utilize some kind of the weak supervision might be is that For example, like for some kind of the geometric primitives, we can use the geometric discrete shape itself as kind of the some supervision. So when you have a set of some kind of the geometric primitives, we can check whether this kind of the set of the geometric primitives are fitting well to the given the geometry. So that can be very weak kind of information that we can utilize to in terms of against some kind of the some of the primitives. Or we can also consider using some kind of the possible deep variant to the given shape. So this is also our work, which is learning basically the optimal set of the control points that can produce all some kind of the possible variations of the given shape. In this case, like without having some explicit the supervision for the control points, by only using this kind of the possible variant of the given shape, we can also learn this kind of the set of the key points that can best fit to each of the kind of the given the target shapes. Also, this is another example that we are learning some kind of the parts, and also there are associated motions like the rotation for the transformations based on kind of the animations of 3D point cloud in the scene. So this is another example that we are utilizing kind of the with supervision to learn the not only the parts but also the associated motions as well. And one basically work that I want to basically introduce in this talk is that the learning this kind of the part composition using some kind of the holistic linguistic description. So when you think about basically take some parts for the 3D shapes, they might be really basically time consuming and also the labor intensive in terms of the user needs to basically annotate each of the parts using this kind of interface. But if we ask the people to basically provide some kind of the description for each of the 3D shape, they might be much easier because the human can just like say something about the 3D shapes without using any kind of interface. And now we are seeing many kind of the new data set, which is not providing any kind of the part level annotations, but some kind of the global text description for the shape. So those are some kind of the example, which is the shape quality data set, and we also extended this data set into the much bigger site, which is the shape quality data set. So those are the cases that we are having some sort of the some global text descriptions for these 3D shapes. So in the work that we presented in this paper 2022, the idea was that basically how we are going to utilize these kinds of sort of the lengthy descriptions for the entire 3D shape in terms of like discovering some semantic parts. So in this example, the input is basically having some sort of some description, the text description for the entire shape, and then we are discovering this kind of some semantic parts based on that. So here the key idea is that we are utilizing basically the reference candy idea in terms of collecting some the text description. So the thing is that now we are not only having the target shape, but also some kind of the destructured shapes, and we are also having the two people. One is the speaker, and the other one is the listener. So here basically the setup is that the speaker only knows which one is the target shape, and where the speaker is basically describing the target shape in a way that the listener can find the target shape out of these kind of destructors. So let's think about this setup. So the speaker knows that the leftmost one is basically the target shape. Then what the kind of the best way to describe this kind of target shape? So there can be multiple ways that we can have some kind of a description. For example, we can say that the target shape is the only one that has the armrest. Then we can maybe say that the target shape is the only tallest one. Or this can be also kind of one example. Then the speaker can say that the target is the one that has the furthest in the legs. So the thing is that if we collect some kind of some global text description in this way, then what we can see is that the speaker will try to basically provide some kind of description for some kind of the distinctive parts that can be used to basically find the target shape of the distractors. So basically, this is our key observation. If we basically collect some kind of the text description of the chairs or some of the 3 objects here, using this kind of reference can be set up. Without having any kind of some sort of the interface that the user needs to basically annotate some kind of part of the shapes, we can basically collect some kind of the descriptions, basically describe some kind of the distinctive parts in these 3D shapes. So our key idea is that we are collecting lots of these kind of the text descriptions for these 3D shapes using the reference scheme, and then we are making a neural net that can basically replace the listener in terms of defining target shape with the destructors using some kind of attention demotion. So here the setup is that as kind of input, we are providing like one sentence, which is describing the target shape, and then we are providing also the bunch of the shapes, and one of them is the target shape. And we train a basically neural network, which is basically the classification network, finding the target shape, given the basically text description. And while we are basically making this kind of neural network, we are having the basically the authenticity model, which will basically highlight the parts which is associated with the basically description. So here basically the high level the idea is that we're having the text description and also kind of 3D model, which is represented with kind of as a set of these super segments. And then we are having some kind of encoder for both of the text and the 3D shapes, and having the attention model, which is basically highlight some kind of the parts over the 3D shape, which is associated with each of the words, the token into the text. And then we are basically feeding this kind of the feature into the output, the another input of the text, and then basically getting some kind of score, like how likely each of the shape will be the target shape in the text description. So this is like the very simple the idea why there's a bunch of the details in terms of the some implementation architectures. So you can also check out those details on the paper. But here basically the idea is that if we have this kind of the some description, then we can also get some really high quality some segmentation results without having any kind of supervision for each of the first. And also in terms of some quantitative evaluation, obviously we are not reaching some kind of vectors that we can get with this supervised learning, but we are still getting some kind of the 8% kind of the vectors for the shape maturity segmentation. And the good thing is that this can be also, generalizable to the many kind of other kind of categories as well. And we can also use the same idea for the fine grained parse segmentation. So this was kind of the idea in terms of how we can split the 3D object into the parts. So we consider many different representation for the parts, and also think about like many different some kind of the some strong supervision or the weak supervision for the kind of splitting the parts. So the next part is basically how we are also going to build this kind of unique parts. Also, obviously, there are many kind of some interesting data set in terms of providing some kind of the information about the relationship of the parts. But our focus was to basically how we get obtain this kind of relationship information of the parts without having any kind of the explicit supervision. So in this example, we focus on that to learn some kind of the full variability in terms of when we basically vary each of the parts, how the other parts also should vary in terms of the correlations of the parts. So for that, in our basically 3.21 we basically try to basically learn this kind of meta handle, which is basically giving some kind of more intuitive handles for the deformations, while also capturing some kind of some co-variability of the parts. So you can see that there are some kind of some let's say movie here. So depending on how we basically control each of the handle, you can see that we can make some kind of more intuitive deformation. So basically, the first we did some kind of previous work is that previously we are using some kind of the key point or some kind of the primitives as kind of deformation handles, which is basically some like geometric handles, which is not capturing kind of some semantic meanings. But when we have this kind of some intuitive deformation handles, then we can basically factorize or some kind of some plausible deformations while capturing some kind of the correlations or some kind of the deformation handles. So the base idea for that is basically learn some kind of dictionary of some kind of key point movements, some kind of a conditional gain idea. So if I skip some details here, so basically the given idea is that given some kind of a set of the control points, we are learning some kind of the meta handles, which is represented as some kind of a combination with translations of the control points, and then the final deformation is basically represented as also the linear combinations of like those the meta handles. And to learn this kind of things, we are using some kind of the conditional dance sort of architecture, which is first producing some kind of a set of the meta handles and produce some kind of the random deformation. And our discriminator is basically checking whether the random deformation is really making some realistic shapes. And also we are having another some part of your network which is basically avoiding to make some kind of the rest of the shape as kind of the final output of the deformed shape. So those are some examples of learning some kind of some intuitive handles of deformations. Yeah, we also provide some kind of a demo for this kind of the deformations. So the last part of my talk is about the combined this kind of parts. So I think I have to very good for this part. So let me go keep on with this one. So I also have some kind of some other works which is like generate some kind of 3D objects by rotating some parts and also assembling those parts to make some kind of a new shape. But those are all the cases basically we are basically doing some kind of retrieval to basically produce some kind of a new shape. So those are all the cases that we are making new chair by retrieving to the part from the given 3D database. So here the question we had is that how can you also generate some kind of these 3D shapes by generating both the kind of the part of the structures and also some kind of the upper parts geometry simultaneously. So if we see some kind of the recent work of like 3D generation using diffusion models, those are all the cases that we are basically generating some 3D shapes with some kind of the representations of the point cloud or the voxels. So for those kind of the cases, we cannot do some kind of editing with the final outputs. So here the question that we had is basically that we had in our the ICCVT paper was basically how we can basically utilize some kind of some part level some representations in terms of that we are making some diffusion model that can produce many kind of diversity shapes, but also allow some kind of diversity applications like the part level decomposition or the probability mixing is like taking the red parts and the green parts and making some kind of new shape, and also do some kind of text 3D generation and also the text ID departed. So in this work, the main idea is that we are basically utilizing some kind of the hybrid representation, which is basically describing both the global, the top level the structure, and also the upper geometry as well. So we are having this kind of some ellipsoid origin the parts, and also some kind of latent feature that can be decoded into each of these specific geometry. So to train this kind of a diffusion model that can produce this kind of representation, we also utilize some kind of the cascaded diffusion models, which is first producing this kind of some explicit the structure in the part level, and basically also producing some kind of the implicit some representations for defining the geometry. So here the key idea is that we are having taking advantage of both the explicit and implicit representations in terms of that we can apply some kind of some editing, some kind of the techniques using the image diffusion models. So we could see many kind of recent work which is utilizing some kind of the pixel space, the image diffusion model for some kind of painting or some kind of editing. Which is basically all the cases that combine some kind of the forward process and the reverse process of the diffusion models. So the good thing of having some sort of the hybrid representation of the explicit and implicit representation is that we can apply those kind of techniques for this 3D as well, having some kind of the completion or some kind of part mixing, while basically achieving basically the best quality in the generation. So yeah, those are kind of some lists of the work that I also worked on in terms of the composition in this 3D. And I think there are many kind of open questions for some future research. Like one of the open questions like this that how we can also kind of like scale up this representative composition technology. So we basically use some kind of the work, which is designing some kind of the components based on some kind of the some language description. But which is also the case that we collected this kind of data set from the kind of the people. But how can you also utilize some kind of some foundation models to incorporate those kind of things to learn the compositionality not only in the 3D. So in our the paper that we are going to present on the Thursday, we also basically are going to present this work, which is basically modifying this for displacing the sampling in terms of that we can utilize the image diffusion priors, not only for the generation, but also for the editing as well. So this is kind of example that we are applying the technique for the nerve editing. So compared to the previous work, the good thing is that our work can basically make some kind of some geometric changes, basically like lifting it bubble or some drinking it copy. So those are some kind of geometry cases in terms of editing the nerve scenes. Another example, and the same technique can also be applied to some kind of the some vector image editing as well, like changing the field color into the space middle, for example. So this is the work that we are going to present in our paper that will be presented on the Thursday. We also basically do some kind of the ideas in terms of applying this kind of image diffusion priors not only for the nerves but also for the mesh editing as well. So this is kind of example that we are making some kind of deformation of the mesh. If we only use the geometry information for the deformation, then we're going to see this kind of some distortion in the output. But if we use this kind of some image diffusion priors, then we can see that we can basically fix this kind of the wrong kind of information. So this is also the work that we are going to present on devices. And image diffusion models may not be the only part that we can use. We can also consider many other types of the trials from some kind of the foundation models. So we are also seeing lots of the examples that we are also using the click model or some kind of LLM to basically learn some kind of the composition structures from the same understanding for many other things. And the second, the open question is how we can also learn some kind of the more complex some composition rules. So if we see many kind of human-made objects, then actually you can see many complex structures like some symmetry or some repeating patterns or some orthogonality, some parallelism or coincidence, many other things. So when we think about this kind of some complex rules, what can be kind of the good supervision, the sort of supervision that we can use. So probably like some foundation models can be kind of good source. We can also think about like learning those kind of things from the many kind of different priors. And finally, the last question might be that how we can also incorporate this kind of some kind of parts and the composition rules for these generative models. So many kind of generative models that we are seeing is basically generating some kind of 3D shapes by learning some kind of the patterns of geometry. But if we can start to see basically learning this kind of the composition of the structures in the 3D generation, then I guess we will be able to see much diverse kind of types of the shapes that was basically not possible with the current 3D generative models. So this is the method, end of my talk. So these are also the list of the papers that I briefly introduced in my talk. So thank you for listening.
We are now in terms of basically understanding 3D geometry at the part level to facilitate tasks like autonomous driving, maybe localizing regions where maybe a car may park, let's say park this car between the low Tesla and the Toyota Camry in front of it or something like that. So how fine range can we do this in the front stage?
Yeah, I think the challenge here now might be that so we are having like lots of kind of these data set or some information in terms of learning the compositionality for these 3D things, like for detecting the cars or some kind of trees, many kind of things. I know that there are quite many kind of the large scale data set. But as we go down to the more fine grained level, like having some detecting very small pieces of the parts in the 3D objects, I guess it becomes much more difficult as we have some kind of some data set or some kind of structure for that. So I guess basically how to learn those kind of things, especially without having some kind of some manual efforts for that, like collecting some kind of data set or using some kind of some other source of the supervision might be challenging, but also interesting questions. I don't know, maybe some kind of some image segmentation model or some kind of LLM might be kind of a good source to learn those kind of things. But here the challenge might be like how we utilize this kind of some weak supervision to basically run this kind of composition for the 3D objects.
Thank you very much. Very interesting talk, I think. I have a question about this listener and the other role where you're collecting this data on this person started. So I would be having two questions. How much data that you require in order to use this properly for states? And second, do you think you could use like an image captioning or 3D captioning technique for that when you present these images and you prompt some model to exaggerate the differences or something along this line?
Yeah, thank you for the question. So in this work, I remember that we used the like thousands level kind of the sentences to get the parts, but for this specific class of the sheets, so only for the chairs, we I think collected like thousands kind of the prompts for the description. But we also collected the much bigger size of the data set for many other the classes of the shapes. So which was basically the work that I presented. Yeah, this of the shape talk was kind of the case that we were collecting more than like as far as I remember, like hundreds, thousands of the prompts for the 30 classes of 3D shapes. So they can be also good source for that. But also the second question is that how we can also use some kind of the other types of some captioning kind of things. The thing is that so in this work, the key thing was basically how we can get some kind of quality prompt to this kind of the task. Because if we basically have some very general description and just train the authentication model, then we typically don't get any kind of the good results because the description is describing too many different parts in the single sentence. So here the key was basically how we then the description for the one specific part, which is basically also the distinct part with the other kind of shapes in the data set. And for that, basically we are utilizing this kind of specific the setup, which is called the reference game. In a way that we have the not a single person, but having the two people, in a way that the speaker will try to say some distinct parts that can be basically will be highlighted this kind of opportunity. So actually we spend lots of efforts to basically get a quality, some kind of description which is describing some specific
Muted. So how about now? Is this better? Cool. Yeah, so these kinds of drag-based editing approaches, the limitation so far has been that even if you define a bunch of points on the object, the resulting edit that you get looks a little bit like this, right? So rather than achieving the kind of goal that you want, which is to translate that particular object from one part of the image to the other, what you end up doing is something that looks like this. So it's not very easy to extend these drag-based approaches for compositional editing of images. So in this talk, over the next 20 minutes or so, what I'm going to try to do is to give you a couple of examples from our group where we are trying to address these limitations. The first one is about compositional dynamic 3D understanding, where we are trying to understand dynamic scenes, but not just dynamic scenes as a whole, but also the parts of this dynamic scene. In particular, I'm going to be talking about grasping, object grasping. And in the second part of the talk, I'll talk about some new methods that we've developed for compositional 3D aware editing of objects in images. All right, so let's start with the first part, which is about compositional dynamic 3D understanding. So grasping is actually a pretty fundamental human activity. Imagine how many objects you've grasped since this morning. It's probably in the tens and maybe even hundreds, right? So we grasp a wide variety of objects, hundreds of objects every day. These objects come in all sorts of shapes and sizes. Some may be articulating, non-rigid, and so on and so forth. So unsurprisingly, this is a very important problem of interest in computer vision. We've seen a lot of prior work that kind of does this kind of work. So I talked about these upcoming radiance field-like representations. Can't we just model dynamic scenes, grasps, hands grasping different kinds of objects using these dynamic radiance fields? Yes, we can. And at the CVPR, we have a paper that is essentially a data set of dynamic scenes and a benchmark data set that shows how many radiance field methods operate with this kind of dynamic data. However, the disadvantage is we don't get any kind of compositionality. So we kind of reconstruct the whole scene as a whole. We don't know anything about the parts of the scene, right? So that's something that's missing. In the context of classical representations, if you will, so things like meshes, template models, and so on, there's been an extensive amount of work in computer vision that studies grasping. And I'm not going to go over all of them, but there's probably like a couple of decades worth of work that tries to understand how humans grasp objects, given important applications in robotics, mixed reality, and so on. But the limitation of these approaches so far has been that the representations that we are using today, most common representation being meshes and template models, they are not particularly well suited for grasp capture because first of all, we kind of need to have a template for the hand and the object. So we kind of need to build this compositional representation for different parts of the grasping activity here. And even if we have these templates, they don't end up being very good models of the underlying data that we have, which tend to be RGB images. So this is manifested usually as these misalignments that you see between the mesh and the underlying RGB images that you have, right? So that's something that's pretty common. So in our lab, we've kind of been thinking about how to exploit radiance field representations as representations for grasping. And in particular, we think that radiance field representations are particularly well suited for the grasp capture problem because radiance fields are pixel aligned by construction. So we can help avoid these kinds of misalignments that I showed earlier with respect to these template models and the underlying RGB data. And in addition, they also have the advantage of being photorealistic and so on. So I'm going to quickly talk about a paper that's going to be presented at CVPR on Wednesday, tomorrow, which is about markerless grasp capture using articulated 3D Gaussians, which is a kind of radiance field representation. You can replace this with NURBS or your favorite radiance field representation. The idea is the same. And here, what we'd like to do is we'd like to capture human grasps at a very high level of detail. And we'd like to capture certain components of human grasps. We'd like to decompose grasps into these components. So what are these components? We are really interested in objects. So we don't want to capture the grasp as a whole, but we also want to understand what the shape of the object is, what the appearance of the object is. We'd like to understand something about the pose of the hand, how the shape of the hand, and finally the contact surface between the hand and the object, right? So that's something that we care about. So these are the three components that we want to decompose videos like this into. And this was work that was done by Chandradeep, who's going to be presenting this tomorrow morning. That's paper 196, if you'd like to know more about it. All right, so let's say that we have a grasp scene, right? And you'd like to reconstruct this grasp scene. The first thing that we might be interested in doing is to try to understand something about the object. So given grasp sequences, we can use off-the-shelf tools like SAM to segment hand object separately, right? And once we have segmented the object separately, we can then build these kinds of radiance field representations. So for those of you who may not be familiar, in this example, we are using 3D Gaussian splatting. So essentially, we model the object as a collection of hundreds of thousands of 3D Gaussian functions. Each function has attached to it some properties, including mean, covariance, opacity, something about the shape, as well as about the appearance of these objects. Each of these Gaussians can then be projected onto the source image, a process called splatting or rasterization, and that results in a pretty good reconstruction of the shape and appearance of objects. So the reconstruction that we get looks something like what you see here on the right. Okay, so we've successfully reconstructed objects in these graph sequences, but there are some limitations. So firstly, because we are using these radiance field representations, we don't have this pixel misalignment problem. So we're able to reconstruct these shapes pretty accurately. But the limitation so far is that these representations can't yet capture articulating shapes. We are focusing on rigid objects here. The hand is an articulating shape. We can't extend the same representations to the hand readily. So in order to fix that problem, we extend these radiance field representations to also capture articulating shapes. In this case, this is, again, 3D Gaussian splatting. Given a hand that we might have in a grasp capture scene, we model the hand as a collection of 3D Gaussian functions similar to the object. And we then attach these Gaussians to an underlying kinematic skeleton. The skeleton drives the position and the covariance of these Gaussians, and given a driving pose, so that's the articulation of the fingers of the hand, we can then pose these 3D Gaussians in this new pose that we want to look at the hand at, and then finally rasterize this to obtain some kind of a representation of the hand. And this whole pipeline is trained on a lot of training data using some loss functions, which I'm not going to talk about. But essentially, using this kind of an approach, we've managed to extend this representation to also model articulating shapes. Okay, so here's some examples of how the reconstructions look like. As you can see, this captures both the shape as well as the appearance of the hand. And as the hand articulates, we're able to capture the details pretty well. And this is all being driven only by the underlying kinematic skeleton, the pose of the kinematic skeleton. Okay, so what do we have now? Given grasp sequences, we've managed to reconstruct the shape and appearance of the hand. We've managed to reconstruct the shape and appearance of the object. And we have an articulating model. So we have decomposed the input data into components. Now we can recompose the whole thing together to accurately capture grasps, as well as associated things that we can capture, including contact area and so on. So the way we do this is, we drive the hand model using off-the-shelf hand pose estimators. And given grasp sequences, we can successfully reconstruct using the techniques that I've described earlier, both the shape as well as the appearance of the hand jointly. So we can compose the two different methods that I talked about to jointly obtain both the hand as well as the object accurately. And the advantage of doing this is that we can now start to reason about where contact happens, right? So being able to compositionally reason about these dynamic scenes enables us to extract information such as contact points. So the heat maps that you see here on the fourth column denote where the hand is making contact with the object, where on the hand contact is being made. And the heat maps of the object show the reverse, which is where on the objects the hand is making contact. So we can kind of make these inferences simply by being able to decompose the scene into its constituents. We can also accumulate the whole thing over time. These sequences are temporal sequences, so we can obtain like an accumulated heat map. Grasps are not static. As we grasp an object, the contact points change a little bit, so we can kind of take that into account as well. Okay, so here's a few examples. What you see on the first column is our data. So those are this is a multi-view grasp capture sequence. So we capture a lot of that data. And what you see in the second column is the reconstruction of both the hand as well as the object. And we can, and because this is compositional, we know the hand separately from the object. We can actually make estimates about where contact happens on the hand, which is the third column you see as a heat map, as well as on the object, which is on the fourth column. All right, so this kind of to study this kind of problem, we rely on a lot of training data, and to obtain this kind of training data to build these radiance field representations, we need a lot of views. And in order to do that, we built our own camera capture system. I'm not going to talk about the details here, but essentially this has 53 cameras that is designed exclusively for capturing hand interactions. Okay, so we have this data set, which is called the Manus Grasps data set, which is now public. This data set has 53 camera views. Overall, it has about 7 million image frames. So that's 7 million image frames showing different kinds of grasps. It contains ground truth for the hand shape, hand pose, object shape. And most importantly, it also has a ground truth for contact. So how do we measure how good the contact is? So this is something that we infer from separately reconstructing the hand and the object. So how good is this? So in order to evaluate this ground truth contact, we took inspiration from work from the 80s. Kamakura and colleagues studied hand grasps in particular by painting objects in wet paint. And then they would ask participants to grasp these objects. The wet paint would leave a residue on the hand, and you can then analyze this residue to infer patterns of grasping. So we kind of took inspiration from that. And in this, what we did in our data set is my students painted these objects with green wet paint. And after the completion of the grasp, it would leave a residue on the hand. And you can use automatic chroma keying tools to automatically figure out segmentation of how good the contact is. And this is actual ground truth because this is, there is a paint transfer only if there was contact between the hands and the object, ignoring capillary action. So this allows us to kind of build like quantitative metrics for evaluating how good grasp capture methods are. All right, so that's the first part of my talk where we did a little bit of work on using these kinds of decomposable representations and then recomposing them, which gives us interesting pieces of information about grasp contact points and so on and so forth. Of course, there's a few limitations. So currently we are limited to only rigid objects. So extending this to non-rigid and articulating shapes is an interesting problem. Extending this to multiple hands and also looking at more complex grasping and manipulation could be interesting for the future. And that, of course, involves a lot of different objects, different hands, which we need to take into account. Okay, so in the second part of my talk, I want to introduce some. So the first part of my talk looks at the dynamic scenes question, right? So we have this new emerging radiance field representation for dynamic scenes. How do we also incorporate compositional understanding into these dynamic 4D representations, if you will, right? Whereas in the second part of my talk, I'm going to discuss some recent work we've done on editing 2D images, but doing so in a compositional and 3D aware way. So that's the second topic that I wanted to discuss. So talked about examples, previous examples of these drag-based editing approaches. So these are approaches where like drag diffusion, drag and diffusion, drag-an, and so on, that enable us to edit images based on point selection. So you can select a point on the image and ask the point to be somewhere else. And this produces an edit that is reasonable, right? There's several kinds of approaches, but the limitation of these approaches I showed earlier is that they don't respect, object classes, or they don't respect objects as entities. They kind of treat the whole image separately, so it's very hard to do these compositional object-based edits with these approaches. There's also some other handle-based editing approaches which suffer from the same disadvantages, and also they need depth information as well as language descriptions in order to successfully perform these edits. So we kind of wanted to address these limitations. And we were thinking about what would be an ideal object-based compositional image editor. So what would be some of the things that we might want to do with something like this, right? So let's say you have an image, in this case, an image of a car on a road. We may first want, users may first be interested in figuring out which part of this image they want to edit. So let's say they want to edit the car, right? So this could be easily achieved using state-of-the-art segmentation methods like SAM, right? So it's very easy to get the segmentation masks. They might then want to specify that they want to move this car using sliders. They may want to specify some kind of 3D translation for the car. So for example, they might say, I don't want the car to be on the left side of the image. I want it to be translated in 3D to some other part of the road. So that's something that they may want to do. Or they may want to rotate the car in slightly different ways and so on. Or they may want to completely remove the car from the image, right? So these are some of the compositional editing tasks that they may want to do. So in this work that I'll briefly talk about, my PhD student Rahul has developed this method called GeoDiffuser that tries to achieve these kinds of compositional object-based edits. So what can GeoDiffuser do? So given input images, GeoDiffuser can successfully perform 3D translation. So users can specify that given a selection of an object, how do we translate this object in 3D? So that's something that you can do with GeoDiffuser. You can do it with different kinds of scenes as well. You can also do 2D translation. So you can specify that this object in this part of the image has to be moved to a different part of the image. You can also do 3D rotation. So you can say, I have this dog here, but I don't like I want the dog to look at the camera, right? So you can kind of achieve these kinds of 3D rotation edits as well. So again, I'm not going to go into too many details here because I think I'm almost running out of time. But essentially, we follow the general image editing framework of DDIM inversion. And the idea is as follows. So given some kind of latent noise vector that you have here, we follow the reverse diffusion process, but then have two parallel trajectories or two parallel paths. The first path is what we call, I think I lost the mic here. I'm just going to be loud. The first part is what we call the reference diffusion process, which is essentially just you could think of this as reconstructing the original image back from this noise vector, right? But we also have a second parallel edit diffusion process, which is responsible for achieving the kind of edits that we want to do that the user has specified. So the reverse diffusion process operates as diffusion typically does. The only difference is that the attention layers that we have in this diffusion model are shared between these two paths. So the reference diffusion process and the edit diffusion process share this attention layer, right? And the benefit of doing that is that it turns out that we can cast these kinds of user-specified edits as transformations of these of the attention layers. And I'm going to talk about that in the next slide. But by casting these as geometric transformations of features of this attention layer, we can achieve the desired edit that the user has requested. So how does this shared attention layer work? So we have this attention layer that is shared across the reference diffusion process and the edit attention process. And essentially, we take the user-specified transformations and then convert them into geometric transformations for the underlying attention layers. So that's what you see here on the top here. So in the reference diffusion process, we perform the diffusion, but then we transform the attention layers depending on the kind of edits that the user is requesting. So this could be 2D translation, but it could also be 3D edit. So it could be 3D rotation or 3D translation. And again, I don't have time to go into the details. I'm happy to chat about it offline. But essentially, this, with a lot of other stuff that is part of this pipeline, we are able to achieve this kind of attention sharing between these two paths. And that results in the kind of desired edits that we want to do. Now, one of the challenges is that there's disocclusion. So when you move an object, you also need to fill in the missing part. So we are able to do that as well. Okay, so the most important feature of GeoDiffuser is that this is a completely inference time optimization method, right? So there is no fine-tuning or pre-training involved. You don't have to train the diffusion model. You can use any kind of diffusion model that you have access to, right? And this is, it's kind of like a test time optimization strategy here. And our loss function incorporates losses that try to preserve the background, that try to remove the object successfully, and recompose the object successfully in these images, right? So there is no training or fine-tuning that you need to do. So here's a few examples. On the left, you see the original input image. These are natural images. And on the right, you see the kind of edits that user has performed. So these are all examples of 3D edits, so 3D translation, where we've moved different parts, different objects in this image to different parts of the scene. And one thing to note here is that our method is successfully able to handle shadows and reflections, which we found quite surprising. So in this case, we've managed to move this lounge chair from the right to the left. And you can see that the shadow kind of moved with the chair as well. Right? So that's something that the method implicitly takes into account. We can also do 3D rotation. So in this case, you see that the dog's head has been rotated, the car has been rotated. We can also rotate different furniture, pieces of furniture or animals and so on and so forth. And then finally, we can also remove objects from images completely. So in this case, we've managed to remove some of the objects. And again, here, I want to highlight that we're able to remove reflections and shadows successfully. So in this case, the coffee mug, the shadow of the coffee mug has disappeared completely. Okay, and the same thing, you see that with the boat and the shadow on the water there. All right, so we did a perceptual study comparing it to different methods. Again, I'm not going to talk about the details here, but essentially almost 85%+ of the time, people preferred GeoDiffuser to other competing methods, as well as other methods for in-painting and so on. Okay, so here's a few comparisons with existing drag-based methods. And again, the importance of understanding or operating on images at the object level is kind of evident here, right? So using drag-based methods results in edited images that don't preserve the original object as well as our method does. This is also scalable, so you can use any diffusion model that you like, stable diffusion 1.4, 2.1, doesn't really matter. So this actually works with any kind of diffusion model or any model for that matter, where you can use this kind of attention sharing mechanism. Okay, last couple of slides. So limitations, so there's obviously some limitations of our method, especially when it comes to 3D rotation. Because we need to, with larger rotations, we need to in-paint a lot more of the object, which gets pretty tricky. So that's something that our method isn't able to handle as well. So that's something that we are working on. Sometimes we see aliasing artifacts that we are trying to address, and in-painting isn't always perfect, especially in these difficult kind of scenes with a lot of texture and so on. All right, so takeaways from GeoDiffuser. For me personally, I think geometry, looking at image editing from a geometric perspective and doing this in an object-centric way allows us to unify different kind of editing tasks into a single method, and that's kind of what we showed with GeoDiffuser. And having this compositional capability enables us to perform these edits the way the user desires to do, and you can kind of extend this to multiple objects in the scene and so on. All right, with that, I'd like to thank you for your attention and thank my students and sponsors. And if you have any questions, I'm happy to take them. Yeah, we've done a few experiments. So, one of the things that we can try to do is, let's say you want to rotate by 45 degrees. You can divide that into increments of 5 degrees, let's say, right? Right. I think the problem that we encountered was that the errors accumulate. So every time we do the editing, right, so the image degrades just a little bit, right? And as you keep doing it over and over again, the degradation results in images that maybe are not at the level of quality that we might want to have. Yeah. Yeah, I think there's definitely more things we can do there. Yeah. Question.
This gives us like are these like suppose are these ways on the optimization or
use just the
The weights are never touched. So it's exactly like I described. There's actually not much more technical detail apart from the details of the attention sharing mechanism. So we don't touch the weights at all. So we simply transform the attention layers using the geometry transform from the user specified edit, right? So there is really no change in the weights. You can use the diffusion models as is without any change.
Okay, then let's thanks. Thank you. Next on our agenda is oral presentations. We're gonna have 7 papers presented. So each presentation is gonna have 12 minutes, including questions, and we really need to make sure we stay on time.
Okay. Okay, thank you. Hello everyone, my name is Junpeng Chen. Today I'm going to discuss our CVPR paper named the GFAST gradient field-based autoregressive sampling for 3D part grouping. Due to the traveling issue, I can only deliver my presentation through the online format. And we also include our paper link at the corner here, so you can scan the QR code. Okay, so let's start on my presentation. So to brief introduce the contents, we will start with a brief introduction to our proposed 3D part grouping task. And secondly, we will introduce the gradient field-based autoregressive sampling GFAST to solve this problem. And we will finally introduce the benchmark, which includes the qualitative results and the quantitative results for this task. So let me introduce the definition of 3D part grouping task. So in here, we imagine you have several shapes here, and these shapes are constructed with the parts. But interestingly, these parts are occasional or something else just by case mixed together and shuffled into a mixed part set. And now we want to use some algorithm to automatically separate them and find out all the potential groups from the mixed part set. So this is very challenging for two problems. So first, we don't know how many groups, and here this is unknown. So we don't. So this brings difficulty to define the output of the grouping algorithm. And for second reason, we also need to use algorithm to understand the relationships among all the mixed parts. So we actually we believe the 3D part grouping may have some potential applications. For example, in the archaeological area, it is quite often that pieces are mixed together. So imagine the piece here is the parts of some chairs or tables, and we can use grouping algorithm to find out the artifact pieces and separate them into the groups. And in a very similar way, when you get some mass room or kitchen, we can also use 3D part grouping algorithm to do the item organizing here. And so that's the potential applications of 3D part grouping. But in our paper, we use the 3D paths to do all the experiments. So next, I will introduce our main algorithm called gradient field-based autoregressive sampling, GFAS. So for the core idea, we use a probabilistic method to model the 3D path grouping problem. So to be specific, we use a Boolean vector C here to define the groups, and we try to estimate a conditional distribution P, C conditioned on P, where P represents the input mixed part set. So let me show you more in a more intuitive way. So we have the mixed part P here, and actually all the groups can be represented by a selection vector. So for example, here we have in the first place, here is 2, and we have the groups here is, we include this parts. And for the second part here, and we can also find here, it belongs to the group N, and so on and so forth. We can represent all the groups simply with the selection vectors. And please bear in mind, with this definition, we can actually use a probabilistic way to model our problem. So imagine here, we have the all the possibilities of selections, but only some selections are valid. So we can construct it conditional distribution density function here, which is a discrete, and we have the input mixed parts, and we have the selections to model this probabilistic function. And with this definition, the problem remaining is to use some tools to solve the conditional probability estimation problem. And we borrow the recent proposed score-based, or to say the gradient field-based method to construct our architecture. So we first use a point net to extract the features from the input parts, and we got the per part features FPN. And then we use a gradient field-based selection GNN to construct our log gradient density function. So the GNN here is applied to understand the relationships of these per part features, which is identical. It understands the relationships of input parts. And at every iteration, we can obtain a selection vector. And then use this selection vector, we can obtain our group N, and we also have the rest paths Pn plus 1. We repeat this procedure until we obtain all the groups or the N reaches the maximum iteration. So that is the implementation of our proposed GFAS algorithm. So in terms of the training and sampling, as stated before, our goal aims to estimate the conditional distribution with score-based model, or to say the gradient field-based model. So in this case, we can apply the standard score matching training and sampling algorithm. So our implementation is use the score-based model with SDES. Actually, you can use other implementations such as diffusion model, etc. Okay. So we have we here demonstrate 2 algorithms, which are the standard score-based algorithm training and the predictor corrector sampler for the sampling procedure. For more details, you can refer to the original paper of score-based models with SDEs. So now let me show you the some qualitative results. So we, except from the GFAS, we actually propose another 2 potential algorithms. And with the comparison, the comparison here show that only our GFAST algorithm is able to produce the correct groups based for every possible input set. It is hardly possible to for other algorithms to produce the correct groups. So next, we also want to quantitatively evaluate all the methods. And in our evaluation, we use precision, recall, and F1 score to evaluate the algorithms. And in the evaluation procedure, we match the ground truth groups with the closest groups, and we can calculate the TP, F1, FP. And based on these informations, we can obtain our precision, recall, and F1 scores. And now let me demonstrate the quantitative comparisons. As you can see, the GFAST algorithms achieves the highest performance compared with other algorithms or GFAST variants. So we also conduct application study to research the important components, how the important components affecting the performance of GFAST. So in the table on the left-hand side, we remove the gradient field. We replace the gradient field with simply mean squared root loss function. And we also remove the graph neural network to test whether the algorithm can learn without graph learning. And as you can see, the performance has a great job done when we remove these two important components. The table on the right, we test the sampler with different samplers and different number of steps. And the results demonstrate that the predicted correct sampler achieves the best performance with the sampling steps at 500 steps. So here is the reference for our presentation. Thank you very much.
Thank you so much. Do we have a question for a speaker?
Okay.
No? Okay, thanks. Let's move to the second talk.
Hello.
Can you hear me?
Yeah. Okay.
Okay, thank you. So the second talk is going to be about the learnable Earth parser and discovering 3D prototypes in aerial scans. And the speaker is Romain Loiseau. Yes. Sorry about that.
Should I use the sound in Zoom? Sorry. Perfect. Okay, so hi everyone, I'm Romain Loiseau, and I'll present our work entitled Learnable Earth Parser, Discovering 3D Prototypes in Aerial Scans. Thanks a lot for the organizers of the workshop for inviting me. So to analyze 3D aerial LiDAR scans, most methods either require very expensive 3D annotations, or for unsupervised approaches can rely on abstract feature representations that are often difficult to interpret. And furthermore, most of existing methods are often designed, trained, and tested on synthetic or highly curated data. So in this paper, we introduce an unsupervised framework for parsing large real-world 2D scans into interpretable parts, alongside a new uncurated annotated aerial LiDAR dataset acquired in various environments. So to perform semantic and instance segmentation directly through reconstruction, we learn 3D prototypes alongside a way to position and deform them to reconstruct inputs. Our 3D prototypes are point clouds whose point positions are directly learned as free parameters of the network. Alongside the prototypes, the prototypical point clouds, we will also learn a neural network to select, deform, and position them to reconstruct input scenes. So as you might expect, learning jointly 3D prototypes alongside a way to select, deform, and position them is very challenging. Because firstly, we have to deal with a large variety of objects across different scenes. And secondly, it is very difficult and challenging to separate objects in a scene. And each scene may also have a varying number of objects. So in this presentation, we'll focus on dealing with ambiguous object separations and varying number of objects. In the previous papers, we showed that we can explore the content of very large 3D point cloud collections by learning 3D deformable prototypes, and that the learned prototypes represents well the diversity of objects contained in the dataset. So today, our goal will be to go from one object to more complex scenes, to learn to decompose a scene into simpler and easier components. So to achieve this, we will train a highly constrained model to approximate a point cloud with a combination of learned 3D shapes. So we said that we are able to reconstruct individual objects. Let's try to do this for a scene. So to reconstruct a scene composed of numerous objects, we introduce slot models, and each of the slots will be responsible for reconstructing one object, one specific object instance in the scene. So at this point, the reconstruction model will just be the union of the output of all the slots. So to handle variations of similar objects, we will set the case output of each slot as a deformed version of the case prototype, and our model can now deform and position each prototype, but it cannot deal with varying number of objects in the scene, as it is forced to reconstruct S objects and cannot select the prototypes to be used at each slot. So to deal with this, we will use a probabilistic modeling, and each slot will be associated with, will predict from the input an activation probability, alpha S, which predicts whether the slot will be used in the reconstruction or not. And we do the same for the prototype selection. The prototype used for the slot is determined by a random variable BS. Yes, and finally, the complete reconstruction model is a union of the activated slots, where each slot output the deformed and posed selected prototype. So while this model can reconstruct very complex and diverse scenes, how can we learn alongside the prototypes, the deformations, and the activation probabilities? So to learn the full model, we use a probabilistic modeling of the reconstruction loss. The first loss encourages likely reconstruction of MX to accurately approximate X. So it encourages activated slots to be close to the input. Yes, so to be close to actual points of the input. And the second loss ensures coverage of the input by encouraging each input point to be well approximated, well reconstructed by at least one activated slot. In the end, we use a probabilistic modeling of the reconstruction loss with regularization to ensure that we learn meaningful and accurate prototypes. So to evaluate our model, we introduce the Earth parser dataset, a dataset of 7 annotated scenes acquired by aerial LiDARs in various environments. So it contains a variety of urban, natural, and rural scenes, making it more representative of the diversity of possible use scenarios and comparable datasets. So trained on different scenes, we show that our model can learn a wide variety of prototypical shapes, such as boat masts, wind turbines, or greenhouses. These prototypes provide an immediate insight into the content of these real-world scenes. The highly constrained nature of the deformations prevents slot from repurposing the same prototypes for different objects, making the learned prototypes easy to identify and manually annotate. So after annotating the prototypes, which is very easy because there are very few point clouds, we can use the reconstruction to reproject the annotation onto the input scene to perform convincing semantic segmentation of complex scenes. And by considering each reconstructed slot as a different instance, we can also perform instance segmentation of complex scenes, such as a marina here, for example. So we evaluated our model against others by comparing the semantic segmentation and the reconstruction performances of different methods. And for example, despite its simplicity, a basic K-mean algorithm on the altitude and intensity of the 3D input points provides a strong semantic segmentation performance. Superquadrics method that learns to approximate scenes with an adaptative number of superquadrics can adjust the number of superquadrics it chooses and to some extent their shape. But because it uses a single parametric family for all prototypes, it cannot provide us with semantic segmentation and fails to reconstruct complex real-world scenes. DTI Sprite, an unsupervised image decomposition approach that decomposes elevation image into a set of 2.5D sprites, has a lower reconstruction and segmentation quality, which is to be expected because it doesn't leverages the full 3D of our acquisitions. Atlaset V2 uses a fixed number of learnable prototypical point clouds to reconstruct inputs. It provides good reconstructions, but semantic segmentation fails because of its inability to adapt its prototypes usage to the input. Finally, our method, thanks to our probabilistic slot and prototype selection, we are able to handle inputs with a varying number of objects using only a small set of learned prototypical shapes. So finally, in this paper, we showed that our novel unsupervised method for parsing complex real-world area scans provides strong semantic segmentation results while maintaining interpretability of the prototypes. So we also introduced a dataset of 7 annotated scenes acquired by aerial LiDAR in various environments, designed to evaluate our method's ability to parse complex real-world scenes. And well, to the best of our knowledge, we are the first to demonstrate the possibility of performing deep unsupervised 3D shape analysis on such challenging real-world datasets. Thanks for your attention, and I'm open for questions. If you have some.
Any questions? All right, thank you so much.
Thank you.
Let's move to the third talk, which is going to be Gen Z zero-shot 3D human scene interaction generation. And the speaker is
Okay. Hello, everyone. My name is Lei Li. I'll present our latest CVPR work, Gen Z, the first zero-shot approach to generating 3D human scene interactions. Gen Z does not require any captured 3D interaction data or 3D learning. Given an arbitrary 3D scene, our approach can synthesize 3D humans interacting with the scene from a short text description, like sitting in a rickshaw, walking on a bridge, or sitting on the ground, picnicking. Generating realistic human scene interactions is a challenging task. It requires holistic semantic understanding of both the environment and possible human actions. Therefore, existing approaches rely on carefully captured data of real people interacting in 3D scenes for supervision. However, collecting such data requires expensive, complex setup, leading to limited scene and action captures in existing 3D interaction datasets. This further limits existing approaches to indoor scene interaction synthesis. We thus consider an alternative perspective and pose the following question. Can we achieve plausible 3D interaction synthesis without using any captured 3D interaction data? We propose to distill interaction priors from large vision language models, which show powerful capabilities in synthesizing 2D human scene imagery. Given as input a 3D scene S, an approximate point location P for the interaction, and a short text prompt, we optimize for 3D human body model that is performing the action in the scene guided by a large vision language model. We first render the scene into multiple views to capture the local context around P, and leverage latent diffusion inpainting to imagine possible 2D human interactions in each view based on the input text prompt. Here, we develop a fully automated inpainting process by dynamically generating human inpainting masks based on cross-attention maps of latent diffusion to find the region of interest. Given the 2D interaction hypothesis after the inpainting, we use an off-the-shelf pose estimator to detect 2D poses for the implanted humans. We then lift these 2D interaction hypotheses to 3D. We formulate a robust optimization optimizing for a 3D human body model that is most consistent with the 2D pose guidance. Here, the blue bars represent our optimizable view consistency scores. More concretely, our optimization objective is formulated with the following terms: a pose fitting term for the detected 2D poses and the 3D pose projection, a view selection term to make sure multi-view supervision. In the meantime, we regularize the 3D body pose and shape to promote naturalness. And we also penalize scene penetration and self-penetration. For more details, please refer to our paper. To evaluate the effectiveness and generality of our approach, we collected 8 large-scale 3D scenes, including various indoor and outdoor scenes with diverse geometric structures. For example, a cartoon-style food truck, a gym, and a realistic Venus city. As shown here, our approach is applicable to diverse scene types, including both indoor and outdoor environments. Our approach circumvents the conventional need for capture 3D interaction data and allows for flexible control of the 3D interaction synthesis with easy-to-use text prompts. Here are more generation results. Our approach synthesizes more realistic 3D human scene interactions and generalizes better across scene types when compared to baselines that are either trained on the indoor interaction data or based on 3D human estimation from a single RGB image. In a binary perceptual study, participants show a strong preference for our generations more than 87% of the time. In a unary perceptual study, our generations have the highest realism rating compared to baselines. Further quantitative evaluation shows that our approach achieves the best semantic consistency score, echoing the strong user preference for our approach in the previous perceptual studies. Our approach can generate various plausible 3D human scene interactions when given the same 3D scene text prompt and 3D location input. We further perform comparisons on a recent indoor scene dataset prox-S. Our zero-shot approach achieves competitive generation performance when compared to the baselines that are specifically trained on this annotated indoor dataset. At last, our code and data are available on this website. Thank you for your attention.
Any questions? Right, thank you so much.
Thank you.
So the next presentation is going to be about diff assemble, a unified
Okay, so hello everyone, I'm Stefano Fiorini. I'm presenting today the paper Disassemble a Unified Graph Diffusion Model for 2D and 2D Reassembly. In this paper, we try to solve the problem of placing each individual component in their correct position and orientation to form a coherent structure. Why we decided to focus on this problem? Because since we are young, the reassembly object is one of the skills that we learn. So if we want to believe and to create a general AI, this is one of the key components we should develop. We also find that this application can be really useful, for example, in the heritage and cultural field, where, for example, we can reassemble frescoes and other objects that we found broken. For this reason, we designed this model that is called the Disassemble. Disassemble is a general framework for solving tasks using a graph representation and a diffusion model formulation. The idea here is that we can work both in the 2D and 3D without any problem, because one of the key components is the use of a backbone, that in case is an equivariant backbone. The other key component is the graph formulation. As you can see here, our graph is at starting point is a complete graph where all the elements are connected to each other. We have three elements: the features. So the features are the element generated by our backbone that depends on the task, on the dimension of the task we are working in. For example, if we are working on the 2D, we have convolutional neural network. If we are working in the 2D, we have point cloud. Then we give the position. The position is the representation of the dimensionality of the continuum Euclidean space. And then we have the rotation, the information on the rotation of the piece. To do the process of reassembling the elements, we decide to rely on the use of diffusion. Why? Because we create, starting from a random scenario, we learn how to reverse the process step by step. So as human did, we put step by step in the right position all the pieces. As I said, our approach is able to work both in the 3D and in the 2D scenarios. For the 3D, we use as dataset the breaking bad dataset. This dataset is composed of around 10K meshes from PartNet and 5010K. In this specific dataset, we have, for each object, we have 20 fractures that are designed, and then there are all simulated also 80 fractures. So at the end, you have 100 fractures for each object. In this, as you can see here, we reported some of the results we obtained. We are state of the art in this specific task. There is no trade accuracy between rotation and translation. And we also, as you can see here from the results, we also rely a lot on the use of diffusion process and also to the use of on the use of equivariant backbone, because thanks to these two other components, we are able to attain better performance. We also apply some other tests to see if our approach is working, if the method we are using is working better or not. As you can see here, we saw that the use of the diffusion process on the 3D rotation without the use of specific Gaussian distribution is working better. We also see, as I saw, the use of diffusion approaches is bringing us a lot of better performance. We also try to see if the use of equivariant backbone to rely on the rotation of each piece is something that can give us a really better performance. As you can see, using an invariant encoder or non-equivariant encoder, we obtain better results. And finally, also, we try to see if the attention mechanism we use to define which are the neighborhood of each piece can help us to obtain better results. And here we use a standard GCN. As you can see, we obtain better results in our cases. These are some qualitative results on the 3D. The hours, it's better than the other state-of-the-art SC3 equivariant. These are some other qualitative results. As you can see, like the diffusion process, step by step, try to recover the right position. So instead of having one shot, step by step, we move the pieces. We also test our approaches on the 2D assembly task. We use Celebi, that is dataset contains only faces. And then we have also WikiArt, that is a dataset where you can find different paintings with different contents, such as portrait, landscape. In these cases, we compare our approaches against other optimization-based methods, since our approaches is the first one, is the first learning-based approach that work with pieces that they have a different orientation. So as you can see here in Puzzle Celebi, we obtain the state-of-the-art results, while in WikiArt, the results are worse, due to the fact that WikiArt is a harder dataset, and it's harder for our approaches to beat the optimization-based method. However, when we test another scenario where you have missing pieces, as you can see from the results, the optimization-based method, they drop a lot their performance, while our approaches is becoming the best. So the idea is like here, the idea is like in a real scenario where, for example, you don't have all the pieces of your puzzle, our approaches can rely not only on the visual appearances, but also on the semantic content, and we can obtain better results. So at the end, we are more robust in these kind of scenarios. These are some qualitative results. As you can see, we are still relying on step-by-step definition of the right position of the pieces. So starting from a random scenario, we recover the right position. We also try to see if we can scale up our approaches. As I told you at the beginning, we were using an attention-based GCN. So basically our approaches as, so when we increase the number of elements, we have also an exponential increasing of our, of the memory required. So we apply a sparsity attention mechanism, and we were able to arrive up to 900 pieces with a standard GPU with 24 GB. On the other side, on the right side, we also test how our approach is inference time compared to the optimization-based method. As you can see, the optimization-based method, they grow exponentially when the number of pieces increase. On our case, our approach is scaling linearly, like with a few increase really, with a really low increase. And we also see that there was no reduction in the accuracy. These are some qualitative results on puzzle with 900 pieces. So in conclusion, we introduced diffassembled. It's a general framework for taking the assembly task with graph diffusion approaches. We demonstrate the effectiveness of our method, both in the 3D and in the 2D puzzle. We also demonstrate that we are robust compared to optimization-based method in real scenario, such as missing pieces. We obtain state-of-the-art results in the 3D domain, and we also show that with our sparsity attention mechanism, we can also increase the number of pieces we can deal with. So if you want to visit us, we will have a poster on Friday and after this presentation. So thank you very much for your attention.
Any question?
Are there any consideration for other modalities from the 3D image?
No, well, no, for this work, we already focus on 2D and 3D. We did another work previously where we try to focus also on the 1D. So we have a shuffle sentences and we try to put the words in the right position. But till now, we focus only on these three, in particular in this talk, only on the two, these modalities like. Well, at the maximum, we can assemble 100 pieces. That is the number, the maximum number of pieces that they are given in the dataset. But there are some details. I think one. Sorry. Here. Oh shit. So it's so the data set here contains, it's here, they have 1 million of breakpoint patterns. So we have 1 million of objects.
Okay.
Thank you very much.
Thanks again. Presentation, which is going to be about
Okay, first I'd like to thank everyone here for coming to my talk. My name is Thomas Mitchell. I'm a senior research scientist at PlayStation. Today I'm going to discuss our CVPR paper titled Single Mesh Diffusion Models with Field Latents for Texture Generation, which was done in conjunction with my colleagues Carlos Esteves and Amish Adia. So I'm sure most of you here are familiar with the images, right? However, what is it takes to generalize diffusion to synthesize textures on meshes? Right? Well, immediately we run into two problems, right? The first is the question of the representation of the texture, right? On what domain does it live on, and how do you build a noisy model on that domain? The second problem is a lack of data, right? So many texture-3D assets are geometrically or stylistically unique, upon which large-scale models can be challenging to condition. So existing diffusion-based text generation pipelines generally seek to map textures to a computationally tractable 2D representation, either via iterative rendering, objects from different viewpoints, or by volume representation, followed by encoding into feature maps. So the benefit of these approaches is that standard 2D diffusion models can be applied on top of the resulting 2D representations. However, both approaches sacrifice fidelity. Right? Rasterization scales poorly in aliasing of fine details in the features. And methods that denoise and project must handle artifacts and view inconsistencies. Right? Furthermore, using a pre-trained image diffusion model to circumvent the data scarcity problem produces synthesized textures that may contain unnatural tones or lighting. So here we present original framework for latent diffusion models that operate directly on the surfaces of shapes, enabling the generation of high-quality textures. So our method consists of two distinct novel components. The first is a latent representation called field latents, which maps textures to tangent vector features at the vertices. So field latents offer an effective form of perceptual compression in which a high-res texture, analogous to almost a continuous signal defined over the surface, is mapped to a collection of discrete vector fields taking values at the vertices. So the choice of vector value features over scalar features is critical as they capture directional information related to the local texture, which we show enables high-quality reconstructions. The second component is a field latent diffusion model, which learns a denoising diffusion process in the field latent space. So although our framework is general and can handle standard large-scale diffusion paradigms, due to the data scarcity problem, we circumvent this by training our models in a single mesh paradigm, where we aim to create new variations of texture from a single object. So our approach enables geometry processing applications beyond unconditional generation, including a straightforward notion of generative texture transfer by simply sampling a pre-trained model on a new mesh. So latent diffusion trains a model in latent space. What does this mean? Well, with images, a high-res image is mapped to a low-res latent space using a neural network called an encoder. A second neural network called the decoder maps back from the latent space to the image. So the key idea is that the encoder acts as a form of perceptual compression. For example, a 1024 by 1024 RGB image is mapped to features on a 64 by 64 grid. So latent diffusion uses this to do diffusion in the latent space. Images are encoded to the latent space where the diffusion model is trained,
and samples are decoded to get the generated images. This is very efficient because instead of operating over the high-res images directly, the model works in a much smaller latent space. So can we do something similar with a high-res textured object? So typically, high-res textured mesh, or high-res texture itself might be a 4K image with millions of pixels, but the meshes to find them may only be like 5K to 10K vertices. So our observation is that because of this difference in resolution, the mesh is a natural low-dimensional latent space. Specifically, we can design an encoder that will map textures to features at the vertices. We can use surface convolutions to build a diffusion model directly on the surface of the mesh to generate textures. So to this end, we introduce an autoencoder called the field latent VAE, which maps textures to tangent vector fields on the mesh. So at each vertex, the encoder is trained to map the texture in the nearby triangles to tangent vector features at the vertex. Similarly, the decoder is trained to map back from the latent vector features of the vertex to the texture on the surrounding triangles. So why are we using vector features? Well, it's because they allow us to continuously extend latent features across the mesh in a directionally sensitive way. So to see how this works, we'll look at how the decoder gets the value of the texture at a nearby point Q. So using the relative position of Q and the latent vectors, we build coordinate features which the decoder uses to get the texture value. Specifically, we compute the dot product and determinant of the latent vectors with the relative position of Q to get a collection of coordinate features which describe how Q is positioned with respect to the vertex. So these features are then passed to the decoder, which uses them to get the value of the texture at Q. So critically, we demonstrate through experiments that this approach is far more effective than barycentric interpolation and is key to enabling high-fidelity reconstructions. Okay, so for comparisons, we quantitatively evaluate the representational capacity of our FLVA against two other approaches, the previously state-of-the-art intrinsic neural fields and a modified version of FLVAs serving as an ablation. So INF trains a neural field which predicts texture values from the Laplacian eigenfunctions extended over the triangles using barycentric interpolation. We evaluate the methods on 16 objects from the Google Scanned Objects dataset, which exhibit complex textural details with high fidelity and high frequency information. So the quality of the reconstructions is measured using the average peak signal to noise ratio, structural dissimilarity index, and LPIP's perceptual similarity metric, all computed in the texture atlas. So two sets of evaluations performed on high-res and low-res versions of the meshes with 30K and 5K vertices, respectively, and the latter results are shown in parentheses. So our proposed FLV achieves the best results across all metrics, and this is really because barycentric interpolation is linear, and so it's inherently low frequency. Right? This makes it nearly impossible for it to capture high-frequency changes in the texture across each triangle, regardless of the dimensionality of the interpolated latents. So in contrast, our proposed coordinate-based interpolation is nonlinear and directionally sensitive. So it significantly increases its representational capacity. FLVs allow us to define field latent diffusion models, or FLDMs for short. Simply put, we can encode the textures to vector fields in the meshes and use field convolutions, a state-of-the-art surface network designed to operate over vector fields, to build a diffusion model which will generate new latent features, which we decode to get high-quality textures. So we quantitatively evaluate the quality and diversity of generated textures by comparing it against Syn3DM, which rasterizes meshes to 3D grids and encodes them to 2D triplane features to perform diffusion. The models are trained to generate new textural variations of assets from the Objaverse and Scanned Objects datasets, and these assets were chosen to exhibit complex high-frequency textures. So fidelity is measured by the mean single image Frechette inception distance between renderings of the original and synthesized textures, and diversity is measured by the mean LPIPs between renderings of different samples. So compared to Syn3DM, FLDMs are able to synthesize higher fidelity textures, which is likely due to the former's rasterization of texture geometry to a 3D grid before encoding, which potentially aliases the fine details. More generally, we observe that by operating over an extrinsic domain, extrinsic representation of the geometry, Syn3DM intertwines texture with the mesh's 3D embedding. And so this means that texture and position are so strongly interlinked that textural details appear as repetitions or extrusions of patterns along the major axes. And Syn3DM is unable to produce significant textual variations without modifying the geometry. So in contrast, FLDMs and FLVAEs are intrinsic and aware only of the mesh's Riemannian structure. This allows them to effectively replicate textual details across areas that are only locally similar, regardless of the relative configuration of these regions in the 3D embedding. So in practice, textured objects are often exhibit specific content that is locally attenuated to certain regions of the mesh, which may or may not be geometrically unique. So our FLDMs can be easily extended to condition on user-specified labels that reflect a subjective distribution of content on the mesh. In the simplest case, a user can paint a coarse semantic labeling, which generated textures will reflect, such as the flipper's head and rock base of the seal sculpture here. A similar approach can also be used for inpainting, where a user can paint regional masks delineating portions of the texture which will remain constant. During sampling, the noise latents in the masked region are replaced with the original latent features. This encourages the inpainted texture to agree with the original mask at the boundaries due to the convolutional structure of the denoising network. So last, I'll finish up by talking about my favorite application, which is generative texture transfer. And as we discussed in the paper, FLVs and FLDMs are locally asymmetry equivariant, meaning that they're agnostic to shape deformations that preserve distances. Loosely speaking, this allows them to replicate textual details on locally similar regions, not only in the same mesh, but across different meshes as well. So a key benefit is that we get a notion of generative texture transfer essentially for free, that a model trained in one mesh can be sampled in a second mesh to texture it in the style of the first. In general, texture transfer is a really tough problem that even state-of-the-art correspondence networks struggle with, as shown in the bottom right. However, we get great results without any fine-tuning. We make it work very well. In practice, we find that FLDMs, we can use FLDMs to actually effectively transfer textures even between highly dissimilar shapes, such as from the skull mesh, if you remember on one of the first slides, to these dinosaurs here. Even though these meshes aren't really isometric. So thank you. That's the end of my talk. I appreciate everybody coming here. Thank you so much to the organizers for putting this together. It's wonderful. It's been a privilege to speak here, and I really appreciate it. Thank you. And come see our paper tomorrow in the PM session. Forget the number.
Any questions?
Yes, sir.
So you said you used the Google scanned
Object data set, yeah.
Did you experiment all with the Objectverse XL?
Yeah, so actually most of the meshes for the diffusion are from Objectverse XL. There's only like one we use from like Google Scanned Objects, which is kind of cool. But actually, so for the first set of experiments with the FL, with the VAEs, we use Scanned Objects models. And then for the second set, we basically use Objectverse models. There's not really a reason. We just found cool models from both and ended up organizing that way.
Did you do any sort of filtering on the Objectverse data set?
So that's a great question. So the preprocessing, so I make this look great, but the preprocessing is actually kind of tough, right? Because this field convolutions is essentially a message passing network. It's effective, but it's also sensitive to connectivity. So basically, when you take a mesh, right, the gory details are that you really need to take this mesh and during preprocessing make like 50 or 100 different uniform retriangulations of this mesh, essentially, because you don't want it to overfit to the connectivity. Otherwise, it's this network is just going to learn to say, aha, this one ring is kind of unique connectivity. I'm just going to match its latent feature, and you'll get no diversity texture. So you have to do this remeshing. It's not ideal. I mean, ideally, you'd like to use something like DiffusionNet, which is connectivity agnostic. The problem is DiffusionNet band limits features. So if you try and generalize it to the latent representation, which is discontinuous and can be high frequency, it's going to band limit the textual details. So there isn't, at the moment, a great solution for actually doing convolutional denoising on a mesh, right? This is a separate question about what, it's unanswered in geometry. What is really a good representation that both can handle high fidelity information and not band limit, while also being efficient and fast and connectivity agnostic. So that's an open question that could be, if someone solves that, you can plug this into this paradigm. I think the real thing I'm proud of is the field latents. I think they're an inventive representation, but the convolutional model itself can be improved. And the field latents probably be improved too.
Any other questions?
Yes, sir. Oh, we didn't. That's a cool idea. No, I did that in an earlier paper, but like using TSNE or something to, yeah, that would be cool. I should do that. There's the code is available now on the website. Feel free to take it. There's a pre-trained model. That's a great idea. We didn't do that. It's a little bit tricky because the features are equivariant, right? So you have to pick some coordinate frame, right? Maybe if you look at the invariant components of that, like you'll see in the paper, we compute equivariant and invariant features. Maybe there's some structure there. That's a cool idea. Thank you.
Okay, last call for questions.
Thank you again. It's a privilege.
Great. So the next talk is going to be CNS edit, 3D shape editing via coupled neural shape optimization, and the speaker is Jiangshu.
打这说话的人家起，把他们说白你出新人，新人垃圾，也是可以。This one. Maybe it's this one. I cannot. It's okay. Is it okay? Okay. Let's. Just. Sure. Maybe somebody. So it's fine. So let's change it. Yeah, it's fine. So we can put in. Yeah, we can go. Okay, okay, fine. It's just I mean, check all the some other school. 不是这个东西，快点说呀！咱们起码是打了2个3。Yeah. 来生这里是刚才这个。
Okay, hi everyone, welcome to my presentation. Today I'm going to introduce our work, CNS Edit. I'm Zheng Zhe from the Chinese University of Hong Kong and CMU. And this is a joint work with Jinyu Hu, Edward Hui, Richard Zhang, and Philip Fu. Let's start with the motivation of this work. So as one of the most important applications in computer graphics, 3D shape editing has been widely used in many applications, including CAD design, the metaverse, 3D games, and VR AR. Traditional editing and manipulation approaches typically relies on editing handles such as points, sketches, and cages. However, these techniques typically lack semantic understanding and control. For example, when we edit the hind legs of this horse, the front legs does not adjust accordingly, which is unnatural. To enhance the semantic control in 3D shape editing, existing methods couple the implicit functions with geometric primitives, or to connect a shape latent space with a clip feature space. In this way, they allow us to edit 3D shapes by modifying the primitive parameters or to trace along clip space. However, they cannot maintain the unedited regions and their qualities are far from satisfactory. For example, to edit the pillow of this sofa, artifacts are induced. And in the right example, when we try to use text to edit the back of this chair, the legs are also modified unexpectedly. And motivated by the above works, the desired 3D shape editing should have the following features. First, it's highly desired to have various operators for the flexible editing. And second, it's essential to have the shape understanding and shape semantics to preserve the validness of the shape in the editing process. And also, the unrelated regions should be kept untouched in the editing process. Next, we will introduce our work. Given an input shape, we first adopt an encoder to generate a latent code, and then we use a diffusion unit to reconstruct the input shape and extract the intermediate feature volume. And next, we take both the latent code and the neural volume as a coupled neural shape representation. And in other words, these two components together will represent the input shape. The key insights behind this design are in the following two aspects. First, the latent code is a compact representation which can provide a rich semantics, but it lacks spatial context. And to compensate with it, we also introduce a neural volume to provide rich spatial context for precise editing. Note that these two components are closely related and correlated. On the one hand, we can generate the neural volume given a shape latent code. And on the other hand, we can propagate the loss through the neural volume to optimize the latent code. By considering both the latent code and neural volume, our new CNS representation contains both the semantics and spatial context, which is suitable for semantic editing with precise spatial control. Next, we aim to make use of CNS representation to deliver a variety of editing operators. And taking the copy operator as an example, we can formulate it as an objective function to be applied on our neural volume. The object function contains two parts. The first part is a list of spatial coordinates in the neural feature volume, specifying region to be edited. And for the copy operator, this is the blue region. And the second part is a list of target feature values associated with the spatial coordinates. As shown here, the target values of this copy operator is shown in the red region. And using these two parts, we can formulate our loss function as follows. And for more details about this, and about how we obtain the two parts for different operators, so please refer to our paper for more details. And then we can backpropagate the gradient to update the latent code. And after n iterations code optimization, we can obtain the updated latent code and obtain the final edited shape, like this chair. And by formulating the objective functions as different form, we further provide various operators for users to edit the input 3D shapes interactively with more flexibility. The first one is a copy operator, which enables users to select a portion of the input shape and copy it into some other location in this shape. Notice that we only copy a bar of this chair, but the other bar in the other side has also copied automatically. Next, we introduce a resize operator, which enables users to specify the selected region together with the anchor point for resizing. And we only resize one side of this CAD model, and the other side has also been resized automatically. Besides, we introduce a delete operator to allow users to remove a selected part of the input shape. Notice that after the removal, the rest back of the sofa is still smooth and coherent without a hole. Finally, we propose a drag operator which enables users to edit the input shape by dragging a single point. As shown here, users can easily edit the size of this hole by dragging one point, which is very challenging for existing approaches. All these results are exciting and high quality, which are not achievable for existing neural shape editing approaches. Besides above operators, we allow users to combine existing ones to form new operators. For example, combining the copy and delete operators can result in a cut-paste operator. Finally, we will introduce our experiment. Here, we present some real results of our method. For example, by simply dragging a source purple point towards this target red point, users can resize the cylinder's hole, which is unachievable for existing works. Besides, for the delete operator, when users delete a hole in one armrest, another hole will appear on another armrest automatically. Also, for the copy operator, we allow users to copy these holes and paste them to other locations. Additionally, when we resize one leg chair, another legs will also be resized automatically. Here we provide some visual comparisons between our method and state-of-the-art approaches. Our method better maintains shape semantics during the editing process. For example, in this bottom row shows when one armrest of the sofa is dragged, the other armrest would adjust automatically, and our method can better follow the desired operation with higher fidelity. Quantitative comparisons between our method and other state-of-the-art methods further show that our edited shapes have the best quality for all the metrics. And here are more results for the drag operator it can be applied for 3D avatar generation and CAD model design. And here are more visual results of the resize operator and cut paste operator. And here are more visual results for the copy operator. Our method enables one to choose a source region, which is in red and in a shape, and paste it to a target region, which is in blue. Visual results for the delete operator. Our method allows one to choose a part of a shape and remove it. To conclude, in this paper, we propose a couple CNS representation. Next, we propose a novel CNS co-optimization procedure. Finally, we provide 4 operators for users to edit the input shape interactively. Thanks for your listening.
Thank you. Any questions? All right, thanks again. Then let's go to the next talk. And this is going to be DAE net deforming autoencoder for fine grained shape for segmentation. And the speaker is
Anyone? Stop and share.
Hey everyone, my name is Chimin, and unfortunately, Jiqing is not able to present today due to some personal reasons. So I'll instead present our work on deforming autoencoder for fine-grained shape co-segmentation. So segmentation, when talking about segmentation, people usually think of semantic shape segmentation, where shapes are segmented into predefined, meaningful semantic parts. And one of the most famous work is PointNet, and it's trained with full supervision with respect to the ground truth segmented data. And some other works also explore, weakly supervised semantic segmentation, such as having one semantic label per part per shape for training. And we also have zero shot. So zero shot models can segment the shape with user provided part labels. And they typically relied on pre-trained large vision or a language model to segment the rendered image of the 3D shapes and then aggregate the image segmentation into 3D segmentation. So basically, they all require ground truth segmentation labels for training, and either dense segmentation labels or just a little bit of labels, or priors from pre-trained large foundation models. And on the other hand, when there's no ground truth segmentation as reference, we can still segment these shapes like lots of classic shape segmentation method do, because most of the time we are not guaranteed to have access to semantic information. And there's also co-segmentation, where given a group of shapes, we not only want to segment the shapes into parts, but we also want to have the correspondence between them. And the parts obtained through shape co-segmentation often seems to be semantic aware. And imagine that if a part has many corresponding parts in other shapes, the part itself must be important enough to have semantic meanings. And also, since we don't have any sort of supervisions, classic shape segmentation algorithm usually require lots of manually designed priors, and even more such priors are needed for code segmentation. So in this work, we essentially introduce a new prior for shape co-segmentation, which is made possible by recent progress in machine learning. And we observed that parts in different shapes often have approximately the same shape, which makes sense, because of form follows function, meaning that the shape of an object should primarily relate to its intended functions or purposes. And for example, if you want to design, let's say, a swivel chair or a chair that can move, the first thing we can think of probably to add wheels, right? But you definitely don't want to put wheels like this one because it's unstable. And you probably need something like this one because the chair now is stable enough for us to sit. So the prior we assume in this work is that parts in different shapes should have approximately the same shape. And now the question becomes how to design an algorithm to use this prior. And then here comes the second observation, capsule network. And we are especially interested in its part capsule autoencoder, which is essentially the transforming autoencoder. And this is introduced to learn the first level of the capsules. And for example, in 2D, we have a neural network to predict a set of part attributes and poses from an input image, for example, the A here. And we also learn a set of part templates, and then we can use the learned poses to sort of select some parts from all the templates. And then these selected template candidates are then affine transformed to assemble the shape in the input image. And the chaining can be supervised by reconstruction laws between the reassembled image and the input image. And then the question now becomes, what if we apply transforming autoencoder on 3D shapes? Will it still work? And most importantly, can it give us reasonable part segmentations? So then here's an overview of the idea we just discussed. And the goal is to co-segment a group of shapes. And to achieve this, we want to learn a set of part templates and affine transform them to approximate the ground truth shapes. Then we can segment the ground truth shapes with respect to the parts after affine transformation, for example, using nearest neighbor. And here's the network design. So it's pretty simple. We have a CNN encoder to predict affine matrices and part existence probabilities for each shape. And then for each 3D query point, we apply the affine metrics so that the coordinates are sort of transformed from the global frame to the part's local frame. And for each part, an NLP is used to predict the occupancy value of the input points. And then at the end, the occupancy values are multiplied with the existing scores and then summed together to produce the occupancy of the output shape. And transforming autoencoder actually performs pretty well. We can get like very nice segmentations on this airplane model, and the segmentations on this chair and guitar are both reasonable, but we noticed that there are small fractured pieces in the chair and guitar. And if you recall that ground truth chairs, even for the same part, let's say the armrest, there are different variations in different shapes. So it's not possible to affine transform a template part into all these different variations. Since transforming autoencoder will try to approximate the ground truth shape, these small pieces are naturally generated to minimize the reconstruction loss. But what we want is a more compact shape segmentation. So we add one additional step. After affine transformation, each part is further deformed to better approximate the ground truth shapes. And to this end, we call our method deforming autoencoder. And we only need to do a little bit of adjustment to the transforming autoencoder network. By adding these deformation networks to sort of a wrap point coordinate, and then by predicting the latent codes to condition on the deformation. And training our network is very intuitive. We only need some reconstruction loss to measure the error between the predicted occupancy values and the ground truth occupancy, and the max reconstruction loss to sort of encourage non-overlapping between parts, and a regularization loss to encourage as little deformation as possible, and then a sparse loss to encourage as few parts as possible, so the network can actually generate compact segmentation. And we also have a training trick to overcome the local minima. So sometimes our network will converge into a local minima like this one, where you don't get a good reconstruction, like the curve leg, and we want the leg and the seat to be separated. So what we do is that we reinitialize some parts so that the network has a chance to converge to a better local minima. And this also works if we have redundant parts. For example, we want to merge these two seats into one, and then we can simply reinitialize this part, and then hopefully network can reconstruct the shape with one seat. And now I'm going to show some results and compare with other works. These are the results on the ShapeNet part dataset, and we can achieve cleaner and more fine-grained segmentations compared to other works, especially in this motorbike examples and the airplanes. So our method also outperformed the other methods by almost 20 points in segmentation accuracy. And here are some results on the animal subset observers and defaults. Since our segmentation is clean enough, we can actually construct core skeletons from the segmentation very easily. And remember that for each shape, we predict a part existing scores for each part templates. And we can treat the part existence score as a binary vector and use this vector as key to group the shape into subcategories. For example, shapes that have the same binary vector can be clustered into the same category. So these are some grouping results. Each block is a group, and then we show an example shape from the group and the number of shapes in this group contained. So for example, about 1,700 chairs in the ShapeNet part dataset just have 4 legs, and then about 400 have additional armrests, etc. And these are some example shape in each cluster group. And of course, our method has a few limitations. First of all, you can only segment volumetric parts. So areas, for example, surface parts, for example, the windshield or the roof of the car cannot be segmented. And also we require the shape to be solid, so not hollow inside, like the last example here. And that's all about DAEnet. If you have any questions, please feel free to reach out to me or Zhixing, and thank you.
Questions? Yeah.
Yes, sir.
Each part is single part, not two parts. I mean, for what I understood, you are posting that they don't stop, but how do you improve this?
Right. Let's go back to. Let me go back to network very quick. So we have the affine matrices would sort of bring all the input coordinate into like the local frame, so they're basically in the rough position, and we have the sum reconstruction laws to make sure that they can connect with each other, and the final output is as close to the ground truth occupancy as possible. And then that's how we make sure that each part is connected with each other, and then we don't want them to overlap, because that doesn't give us clean segmentation. So we have max reconstruction laws to sort of encourage the non-overlapping. So you're saying that how do I make sure that, for example, if the arms, it doesn't have a hole inside when doing them? Oh, okay. That's a good question. This we consider a local minima, where like we want one part to represent the entire forearm instead of 2 parts, right? So the way we did it is that we compute the fractions of all the shapes that have, let's say, part I, and we have a threshold. And if the fraction is less than, let's say 10%, that means that this part template is not used, only being used in 10% of shapes, and that could possibly, there higher chance that they are small pieces. So we reinitialize the branches so they have better chance to generate the entire part instead of combining two different sockets. We have to keep doing it. Yeah. No problem. Any questions?
Right.
All right. Thank you.
Yeah. This concludes the part of the presentation. So the next on our agenda is challenges.
Hello, can you hear me? Hello? Hello, can you hear? Okay, nice. Just a second, Chang. Sharing my screen. Yes, please. Okay, can you see my screen? Just a second. Okay, yes. Okay, nice. Hello, everyone. My name is Xiang Li from Professor Mohammed El Hosseini's group. Today, I will be presenting a summary of the 3D Compact Challenge held at this workshop. Our challenge is inspired by a long-standing question: how can we build models that possess a compositional understanding of 3D shapes? When we talk about compositional understanding, we focus on how different parts and materials come together to form a 3D shape. Here, I show an example of a chair. As you can see, the chair is made of multiple parts of different materials. For example, the backrest is made of fabric and the seat is made of leather. As you can see, humans can easily understand part material compositions of this chair. How can we equip computer vision system with the ability to understand compositions in an automatic way? To do this, it's crucial that we create a data set that includes labels for part material compositions. To meet this need, we have developed the 3D Compact dataset and its successors, 3D Compact++. These datasets are specifically designed to foster compositional 3D understanding. First, let's take a look at some statistics from the 3D Compact dataset. When we compare it to ShapeNet datasets, you will notice that 3D Compact features more vertex, edges, faces per shape. This richness in detail is crucial for our goals in compositional understanding. Unlike previous 3D datasets that mostly focus on geometry understanding, our 3D Compact dataset provides a huge amount of stylized shapes. Each shape contains, on average, 1,000 human-verified style compositions. For each stylized shape, we provide RGB point cloud, part labels, material labels, and texture mesh. We also render 8 different views for each stylized shape, 4 from canonical views and 4 from random views. For each rendered image, we provide part mask, material mask, and depth map. To collect this dataset, we hire human annotators to collect 3D shapes and part material compositions. The whole process is guided by 3D experts with detailed annotation guidelines to ensure the quality of annotations. The annotation process includes shape collection, shape editing, shape alignment, part material annotation, shape sterilization, and image rendering. We repeat this process for each shape to get a collection of sterilized shapes and rendered images. Here I show multiple examples of sterilized shapes from the 3D Compact++ dataset. To understand the advantage of our dataset with previous 3D shape datasets, in this table we show the features of commonly used 3D datasets, such as ModelNet, ShapeNet, OmniObject 3D, Observers, and so on. We also compare with datasets with part-level annotations, such as ShapeNet part and PartNet. In comparison, our 3D Compact++ datasets contains a large number of 3D shapes with fine-grained part-level annotations, including both part labels and material labels. We also provide 160 million rendered images, which can be used for large-scale compositional image understanding. Based on 3D Compact dataset, we benchmark several tasks using SOTA methods. Here I show the fine-grained and coarse-grained part segmentation performance using several SOTA methods. We further introduced a new task called grounded compositional recognition, for short GCR, for compositional 3D recognition. We introduced several metrics to evaluate the performance of this task at both fine and coarse-grained levels. We benchmark this task using different method designs, including methods based on separate 2D 3D training, joint 2D 3D training, and 3D-based methods. We provide user-friendly web tools for users to explore the 3D Compact dataset. We also provide APIs for easy data access and usage. More details about the 3D Compact challenge can be found at the workshop website. Going beyond 3D Compact++, we recently completed another project that aimed to collect more 3D shapes from more shape categories and more fine-grained part material compositions. We are excited to share the 3D Compact 200 datasets, which features 19,000 3D shapes across 200 shape categories, each annotated with part fine-grained and cross-grained part and material labels. This dataset contains 90 million stylized shapes and 300 million rendered images. We show visual comparison between 3D Compact and 3D Compact 200. In this figure, we show the distributions of part occurrence at both fine and coarse granularity levels. As you can see, the part occurrence follow long-tail distributions, which pose further challenges for compositional 3D recognition. We also collect 3D captions from part and material labels and build a new benchmark for compositional text-to-shape retrieval. Now let's summarize what you can do with 3D Compact datasets. With this dataset, you can explore diverse 3D tasks, including 3D shape classification, part segmentation, grounded compositional recognition, text-based 3D generation and editing, grounded 3D shape captioning, and text-to-3D retrieval. This is a recent paper about text-based 3D shape editing, published in CVPR 2024. This work is built upon our 3D Compact++ dataset. Here's another work about grounded 3D shape captioning. This work is also built upon our 3D Compact++ dataset. Finally, our dataset can be accessed at this link. Thanks for your attention. Now I will hand it over to Aditya to continue with another part of the challenge.
Hello, can you guys hear me? Can anyone hear me?
Yes, we can hear you, but yeah, and we can see the screen now too.
All right, wonderful. Okay, so hello everyone. I hope you are all enjoying CVPR. So today I'm going to introduce the Visual Shape Inference Challenge. So 3D objects are highly structured, right? This structure actually arises from various aspects, such as interpart symmetry groups, or even from construction plans. And programs are a very natural way to model them. They enforce strict constraints, expose high-level control, and also aid interpretable editing. And I feel like in this era of large language models, it's worth mentioning that they are LLM interpretable and also LLM editable. So the main challenge comes from the fact that manually crafting these programs is expensive, as it often requires human experts who require years of training. So visual program inference is a solution where, given a shape as input, a system automatically infers the corresponding program, which will reconstruct this shape. So in this challenge, we are hoping to compare different approaches for program inference on the 3D compact data set. Basically, VPI for 3D compact objects. Participants will be tasked with creating a system which infers programs that are accurate as well as parsimonious. So in terms of the input of this system, participants can create systems which take many different inputs. They can take mesh, voxel, point cloud, or even multi-view images. We don't restrict that. But the system should give output in a fixed format, which is going to be a program in a fixed DSL, which we are calling CSG Lite. And essentially, CSG Lite allows creation of parameterized primitives, right? For example, these different primitives, including superquadrics, perform Boolean operations between them, and also construct symmetry groups such as translational or rotational groups. So how will these systems be evaluated? The evaluation metric is going to combine two aspects, namely reconstruction accuracy and program conciseness. Essentially, we want to have lower reconstruction errors and have a smaller program. A system which gives both of these would be a better system. We'll release the exact formulation of the evaluation metric closer to the challenge. Now, there are many different approaches to infer programs for these datasets. Popular approaches include per-shape optimization, such as inverse CSG, learned neural search, such as PLAD, and methods which combine learning with per-shape optimization, such as CapriNet. We'll provide a starter kit to get started with some of these approaches. The challenge will be conducted in two tracks, namely a under 30-second track and a under 300-second track. The first track is geared towards methods that may eventually be used for tasks such as real-time shape abstraction, scene abstraction. And the second track is geared towards methods that aid discovery of highly parsimonious programs, though at a higher computational cost. Finally, let's look at the final piece of information. First, the timeline. So around November of this year, many folks in this room might be working tirelessly for their submissions to CVPR 2025, after which you can finally have some rest. But wait, there's SIGGRAPH deadline as well in January. So after that, perhaps people get their rest. So we have decided to have the challenge start from early February and then have it continue till the end of May. And thanks to the sponsors of this challenge, the prize money allotted for this challenge is $2,000. Thank you for your attention. Please send your questions to my email ID. And if you'd like to sign up for a reminder email, please use this QR code. That's it. I'm happy to take any questions if people have some questions.
Any questions? Okay, I don't know if you can hear me, but no, we don't have questions, so thank you very much.
All right.
And great. So now we're gonna have a break for coffee and pastors. That's unfortunately in the other building, as always. But we're gonna regroup at 4 p.m. here for more invited talks and panel. Thank you.
So do I need to unmute myself on Zoom? That's a question. I think just leave it like this. Okay, complete. Okay.
Okay, welcome back to the last session of the day. So we're going to start with the invited talk from Dr. Chow Yuan Ki. Sorry if I mispronounced that. She's an assistant professor in the Department of Electrical and Electronic Engineering at the University of Hong Kong. She received her PhD from the Chinese University of Hong Kong and has worked in exchange at the University of Toronto, Oxford University, and Intel Visual Computing Group. And she's committed to empowering machines with the ability to perceive, understand, and reconstruct the visual world in the open world and pushing their deployments in embodied agents. Please, over to you.
Okay. Okay, thank you. So, okay, so let's start. So I'm Xiaojuan from the University of Hong Kong. So I'm going to talk about some research on trying to simulate the 3D environment from videos. So before I go into the details, let's first look at why we need this. So in the past decade, we have seen a lot of success by models learning from internet data, right? So we have developed different architectures. We have different models with high capability, like GPT-4a and Gemini. And this success can be all attributed to learning from internet data. But this type of learning paradigm has some drawbacks. First, it's a passive, right? So the model learn from a static data set. This is different from how humans learn, right? Our humans will learn driven by our curiosity, driven by our intention to accomplish a task. And also, in terms of inference, the existing paradigm is also open loop and link interactions with our 3D physical world. This is also fundamentally different from how humans leverage our intelligence to interact with the world. We actually will have a closed loop interaction, right? We interact with the environment, and the environment will give us feedback to help us refine our predictions and so on. So, general agents in our physical world actually learn by interacting with the 3D physical world instead of learning from a static data set. We learn actively and understand actively in the 3D world. We learn through interacting with it. Then the learned knowledge are further utilized for us to better interact with the environment. But how can we replicate this kind of learning paradigm within machines? If we directly expose machines to the real world, it will cause a lot of mistakes, right? It's unsafe. And they are also suffer from scalability issues. If we directly let machines to learn from interacting with the real world, it is very expensive, not scalable, and unsafe. So this is the reason that we need a 3D environment creation. We need to use some approaches to recreate a 3D world within machines so that machines can learn from virtual 3D world. So this is our motivation. So although it is very promising that if we can allow machines to learn in the virtual world, we can have a high scalability. We can be more. The learning can become more safe. But the interactive 3D environment are very rare. It's very difficult to scale up. How can we acquire a 3D interactive environment? This is different from how existing models are trained. They trained on image data set. But the image data are very easy to acquire through internet, right? However, for the 3D environment, we can only afford to capture thousands of 3D environment, and they also have a very low diversity. So you can see in these examples, they are typically household environment, and the diversity, lighting environment, and object arrangements are also have limited variabilities. This is because in order to build a 3D interactive environment, we actually need to specialize the sensors like such as Kinect and LiDAR to capture data and then go through reconstruction and post-processing. So this paradigm, this kind of data capturing process is not scalable. So currently, we can only have a limited number of 3D environment for agents to learn from this environment actively. So in my research, so we would like to seek another paradigm. We want to seek a solution that whether we can turn a video into a interactive 3D virtual environment. So the video data can be easily crowdsourced from the internet. This can offer a lot of benefits. So firstly, the diversity can be significantly enhanced because the videos can be crowdsourced from the internet. In the future, it can be generated by diffusion models. And the second benefit is scalability. With videos, with only monocolor videos, we do not need additional sensors for data capturing. And also controllability. If we can build an interactive environment, we can make it be more controllable, and we can rearrange the objects to create more diversified 3D environments. But this is definitely suffer from a lot of challenges. So the first challenge is you pose the data. So visual clues alone can be very ambiguous if we want to leverage it for recovering the 3D geometry. And secondly, so the representation. So what's the best representation that we can that can be utilized to represent a 3D scene in order to facilitate optimization for learning from a video? And the third challenge is that is the natural dynamics in videos. So in videos there are a lot of dynamic objects. So how can we recover the 3D world and at the same time to recover the dynamics of the objects to create a dynamic 3D world? So these are the challenges. So in order to tackle these challenges, so we have divided this problem into several steps. The first step is we can develop some models that can convert RGB videos into RGBD videos. So with this depth clue, we can bypass the you-pose the data problem and have a better chance to recover the 3D geometry from videos. And given the depth information from images as a clue, we can develop some 3D surface reconstruction method that allows the model to learn from videos and the depth information we have acquired in the first stage to help us better resolve the ambiguities and do better 3D surface reconstruction to obtain a 3D environment. And if we want, so the third part is to make this environment to be interactable. So we care about how can we decompose different objects after reconstruction, so that the objects can be rearranged and can be we can create new environments. And lastly, is to handle the dynamics of real world scenes, that we would like effective methods that can effectively handle real world dynamics in videos. So I will go through this, some of the works in my group following this traditional research. So the first is depth from monocolor or stereo images. So the task is that given the input images, we would like the model to output to estimate the depth given these images. So given this task, a natural solution may be if we can plug in deep neural network and treat this as a simple regression task to output the depth values, right? But the depth is actually a projection of the structured 3D surface onto the image plane, right? So the depth values, they are constrained by the underlying 3D surface that are generating these depth values. So in this work, we would like to incorporate the regularization from surface normal. That is another attribute that reflects the 3D the structure of 3D world to regularize the estimation of depth, so that it can more can faithfully reflect our real world surface. So in this so depth and surface normal, they are actually geometrically connected. So like if we have the depth, we can convert it into 3D point cloud, and then we can estimate the normal from the point cloud. And if we have normal, the normal determines the plane information, and it can constrain the distribution of depth. So in this work, we incorporate the geometrical constraint between depth and surface normal to have a better model that can help us to obtain depth that can more precisely follow the structure of 3D world. So we incorporated this depth to normal and normal to depth constraint into the model design, and then train this model supervised by a depth and normal ground truth data. So these are some results. So you can see with this normal constraint, we can have better reconstruction results if the depth is visualized as a point cloud. So you can see here the planes are flat, and we compared with the baseline approach. Okay, and this also we can have better point cloud reconstruction if we have this kind of regularization on depth prediction. And this is the result on the outdoor scene. So you can see still our approach can better recover the 3D point cloud that has a better quality than the baseline approach. Okay. So this is the one work. So, but when we do this work, we check the data, but we find there's an issue. When we check the ground truth data to supervise training the model, we find that the ground truth data are not accurate. For example, in this data set, this is the KT data set. The data are captured using LiDAR sensors. It is it's not only time consuming, but it takes a lot of resources. But even after very complicated post-processing steps, we find that the ground truth cannot align with the original image, and the ground truth has a lot of mistakes. So depth ground truth is really hard to acquire. So even for using Connect, there are a lot of mistakes and a lot of areas that do not have accurate measurements. But at the same time, we have the computer game engines that can produce synthetic data without relying on human labors. So you can see the quality of the synthetic data that can provide dense ground truth depth information with very accurate boundaries that are precisely aligned with the images. So in this work, we explore whether this kind of synthetic data can help us to do depth estimation. So in this work, we study this in the stereo image setting. The input is a pair of stereo images, and we would like the model to output the disparity map that's similar as depth is the inverse of depth. And the core idea is to use the synthetic data because synthetic data have high quality, and also it is scalable, and we can collect it without so much human investment and efforts. So our initial experiments using synthetic data already achieve surprisingly well results. We can get a very accurate depth estimation using only synthetic data. To further enhance the result, because the synthetic domain and real domain has a gap, we further develop some strategies to address the domain difference between synthetic and real data. So the first strategy is to do domain normalization. So we normalize at both the image level and pixel level to remove the style and texture differences between synthetic and real domains. And another modification of the architecture is to develop a structure-preserving graph-based filtering to encourage the model to extract global level information for prediction instead of relying on local information. This is because when we look at the synthetic and real data, globally, they are very similar, but locally, for example, the texture, they may be very different. So we would like the model to try to extract global information instead of relying on local information that has a large domain differences. So let's see the result. The model is trained purely on synthetic data, and we directly test it on real data. So this is a video from Cityscape dataset. We don't use it for training, and this is the result from classic method as GBM, and this is the model that trained on a KT dataset using human captured ground truth, and this is a model trained purely using synthetic data. So let's look at the result. So it's obvious that although we only use synthetic data, the quality of the depth estimate, the result is much higher than the approach that use real ground truth, real data captured data. And you can see the details and the boundaries of the depth information is much more clear than previous baseline approaches that rely on human captured ground truth data for learning. So this research do tell us that the synthetic data is especially valuable for geometry estimation tasks because capturing accurate depth is an infeasible problem if we rely on sensors like Kinect or LiDARs. And also it often you rely on very tedious post-processing steps. Every step of the data capture is prone to making mistakes. So synthetic data do help a lot. So for depth estimation, recently we have also seen a lot of advancements. Like in this CVPR, we have the Marigold paper. This work, actually, the model is also trained purely on synthetic data. But although they produce very sharp results, when we look at a single frame, the results quality is very high. But if we look at the result across different frames, the scales are inconsistent. So you can see there is significantly flickering. This is because the scale will drift frame by frame, and the model is only capable of producing relative depth. That is not what we need for 3D reconstruction, right? We need accurate metric depth. So in comparison, like there are also some works also in this CVPR, the unit depth work that we can say, although the quality is not as good as like Marigold, but its consistency is much higher. So actually, this is very important if we really want to turn a RGB video into RGBD video. We want a consistency across different frames. So the next step for depth estimation, so our future work will to explore whether we can obtain video consistent metric depth. So it's definitely need us to understand the camera models, because the intrinsics of the cameras will determine the image and the depth your data will have. Okay, but in this part we would like to emphasize that synthetic data are a very important resource if we really want to recover depth from images or from videos. Okay, so this is the first part. So any problems? Okay, cool. So with this depth information from images or from videos, they actually can provide a very good regularization for 3D surface reconstruction. So let's go to the second stage, that is to turn RGBD into a 3D surface. So the first problem is about how can we represent a 3D surface. We definitely can have different approaches, right? We can use point clouds or voxels and meshes. So and also there is another representation, the implicit representation. It represents a 3D surface as an implicit function. It offers high resolution and high scalability, and importantly, it's continuous. So this is especially beneficial if for us because we want to get a 3D environment. So we wanted the representation to be continuous, to be more closer to what the real world geometry look like. So in this implicit representation, it will use a function to represent the surface. This function value is negative if the point, if the location is inside the surface, and is larger than 0 if it's outside the surface. Then the surface can be iterated by applying by obtaining the 0 level set for this function. Okay, so this is the representation that we use for 3D surface reconstruction. Let's look at the approach. So given this representation, so the goal is to learn an implicit function to represent a 3D scene from multiple posed images. So we have RGB data, a video as input, and we would like to train an implicit MLP function that can output either volume density or occupancy or SDF value to represent the surface. So previous research has shown that using the SDF value as the output will give us a better surface reconstruction quality. So we also use this as the prediction. So another paper, mono SDF, has also demonstrated if we incorporate depth and normal from monocolor depth estimation approaches to supervised training, this implicit function will gain a lot of advantages for surface reconstruction. So this monocolor depth and the surface add a strong regularization for learning a surface, especially for thin level 3D reconstruction. But if we look closer into the prediction results, we will find that so there are a lot of missing detail, the missing or detail structure here. So this the detail of this chair is missing, and also there is a black bench here is also missing from the reconstruction. So this motivates us to investigate why this happens. So we find that this SDF-based representation suffer from two problems if it is applied to thin level surface reconstruction. The first limitation is the color bias problem. So we find that the optimization is biased toward high intensity areas and make the low intensity areas like the black areas to be under optimized. So for example, you see, let's see in this case, so for the brighter areas, they will typically have a large gradient magnitude. But for darker areas, the gradient magnitude is very small. So this makes the model prediction will miss reconstruction of the areas that have the low intensity values. So this is why this bench is missed from this reconstruction. And another problem is the bias of SDF-based formulation if it is applied to thin level 3D reconstruction. So we have done a simulation experiment. We use the ground truth SDF field of this scene that consists of multiple objects, and use this ground truth SDF to render depth. So its render depth is also divides from the ground truth depth. But we use depth as a supervision to train the model. So this kind of bias will make the optimization to be biased toward the larger objects, because the larger objects will occupy most of the gradients. So this is the reason why some small structure of the reconstruction is missing. So in order to solve this problem, we propose two strategies to address the two problems. The first is that to avoid the bias to high intensity areas, instead of using color rendering loss, we use this feature rendering loss. We render features, because using features we will not have the low value issue, and we will bring back the optimization signal to supervise training of the low intensity areas. And to address the limitations of the SDF-based representation on thin level 3D reconstruction, we incorporate occupancy-based supervision to again bring back supervision signals for detailed areas. So let's see the result. The left one is the result from mono SDF, and the right one is from the reconstruction from all approaches. So you can see many of the missing many of the objects are missing with this mono SDF based reconstruction, but all approach can recover the reconstruction of these areas and can have a more complete reconstruction. You can see the result. You can see a lot of small objects are missing from the original baseline reconstruction, but our approach can recover and obtain a more complete reconstruction. But honestly speaking, so although we have alleviated this issue a lot, but this is still a problem for thin level 3D reconstruction. So this we believe this is because of the representation. We need a new representations to represent the surface if we want to model thin level for thin level 3D reconstruction. Okay, any problems so far? Okay. Let's move on. So with the reconstructed 3D surface, you can see all the objects are still not interactable, right? It's still a scene that represented by a surface, and all the objects are embedded together with the whole scene. It's not interactable. So the next problem we tackle is how can we make this reconstructed environment to be interactable by decomposing the objects from the environment. So the goal is to want to extract individual instances or objects from the reconstruction so that objects can move and can be interactable. So, however, if we want to achieve this goal, we need to annotate the object masks across different views in the whole video. This is a very challenging task and is also time-consuming. But fortunately, now we have large foundation models like the segment anything model. This can be leveraged as a tool for us to do better object extraction without relying on human annotations. So this is what we do. So given the 3D surface reconstruction, we will extract individual objects. These objects can be further processed with some retexturing techniques to get diversified 3D assets, and we can rearrange the objects to create new 3D environments. So let's look at the technical details. So the first stage is similarly as what we do in our previous work. We do implicit surface reconstruction. Two differences happen here. The first difference is that we also separate the background from foreground at the implicit surface reconstruction stage. And another one is that we will distill the features from the segmented anything model to the implicit feature field. This is two modification of our previous approach. And after this stage, so we will have the 3D surface, but the objects are still not separate. They still modeled together. So we have the second stage, that's to extract individual objects. So here, as we already distilled the same features here at the feature field, so a very simple idea may be we can do feature grouping, right? We group features together to extract objects. But we find that the distilled features are not sufficient for us to separate individual objects, because you can see here, although they are different object instances, they actually have very similar same features. So motivated by this, we introduce the second stage. We introduce the second stage, that is to okay. So we use the second stage. The second stage is an explicit stage. Given the surface reconstruction from the first stage, we will first extract meshes. Extract the surface mesh here. So the mesh has a good topology. It has the vertices are connected in regulated by the surface. And we also will render the features from SAM, from segmented animation model. And also we will ask users to click on one object. And to by combining this click that is from users and the rendered features from SAM, we can feed them into the SAM decoder, and then it will output the mask for the object. But it should be noted that this mask is only for one view of the object, right? So, but we want to extract the whole object from 3D. So the next step we do is to lift this mask into the 3D mesh. To use this mask as seeds for the object. Then we do surface growing on the 3D mesh to extract this individual mesh for the single object. Okay, let's move on to the result. So this is the colored mesh. This is from the first stage, the mesh reconstruction, and this is the mesh result. And this is the distilled SAM features. So you can see if we only do grouping, we cannot separate objects. So this is the decomposed result from our approach. You can see individual objects are decomposed. We can move these objects. And adding new objects into this environment to create a new environment. And then add new textures, add textures on the mesh to create a new environment with diversified textures. Okay. So any problems? So in this part, so we actually have shown that implicit surface reconstruction can help us get a good surface. But it often will sacrifice the rendering quality. If we have a good surface, it often suffer from the rendering quality. So for example, in this example, the big is a new implicit surface reconstruction approach. It can have a very high quality surface reconstruction, but the rendering quality is much lower than 3D-GS, a new representation for non-wheel synthesis. So the next question may be, how can we simultaneously achieve high quality surface reconstruction and new rendering? Like you see, for the Gaussian splitting, it can deliver high quality rendering, but the surface quality is very low. So how can we combine the best of both worlds? So as we think this is the next question. And also we have some preliminary observations that there is a contradiction between the low frequency surface and the high frequency appearance for rendering. So like in this example, this is a ground truth surface mesh, and this is the mesh extracted by using Gaussian opacity field. So you can see this is from Gaussian. So you can see in order to reflect these high frequency details, there will be some noisy reconstruction. So there is a natural contradiction between the low frequency surface and the high frequency appearance. So the next step in the future we may explore is what's the new representation to achieve a good trade-off between reconstruction and rendering, that we can simultaneously obtain high quality reconstruction and high quality rendering. So for this problem, there is a lot of research that worth doing, that how can we decouple geometry and appearance, or maybe we can have some hybrid designs in the future. So we actually have some preliminary results by combining implicit surface reconstruction with Gaussian splitting. Yeah, that achieves reasonably good results. We're still working on this direction. Okay, cool. So the above is about surface reconstruction, but they are all from static images, a static video. So there are no moving objects. So the next problem is, as the videos often contain a lot of dynamic objects, the next question is, how can we handle the dynamics in real-world scenes to reconstruct the dynamics of real-world scenes? So in this problem, actually, this Gaussian splitting, due to its explicit nature, it is very suitable for modeling dynamic scenes because we can drive the Gaussians to move in order to model the dynamics of the real world. Initially, Gaussian splitting is not designed to handle dynamic scenes. So in our work, I will introduce later, we develop a new approach, one simple approach to make a Gaussian splitting capable of handling dynamic scenes. So the question is, how can we make a 3D GIS be able to handle dynamic scenes? So a very natural idea might be we can, for each of the Gaussians, we can let it to have a time-varying 6-DOF transformation to model the movement of Gaussians across different time steps. However, as we use only monocolor supervision, we find that if we allow every Gaussians to have independent 6-DOF transformations for model movement, there will be a lot of noisy Gaussian trajectory, and as a result, the rendering quality is also lower. You can see it's a blurred rendering result. So motivated by a simple observation that our motion patterns in our real world are often sparse, they are spatially continuous and locally rigid. So we ask whether we can use sparse representations to drive Gaussians to move. So in this work, we introduce sparse control points for modeling the dynamics of Gaussians. So the idea is pretty simple. So we have 3D Gaussians. We will firstly introduce control points. That's one sparse, a few control points. And for the control points, we will have an MLP that takes the position of the control points as input and conditional on the time information to provide to predict a 6-DOF transformation for each of the control points. So this MLP will model the dynamics of the control points. And then to drive the movements of the Gaussians, for each of the Gaussian, it will look at its k nearest neighbors. And the 6-DOF transformation of the k nearest neighbors will be interpolated to generate the 6-DOF transformation of the Gaussian to make it move. And then all the Gaussians will have related 6-DOF transformation that will change across time. We will do rendering to render images, and this image will be compared with the ground truth video data for learning. So at the same time, we will also we also design some pruning and densify strategies to control the control points to make it capable of handling different levels of motion complexities. So finally, after training, we found that we can use around 500 control points to drive 100,000 3D Gaussians. So the underlying motion patterns are essentially sparse. So these control points are learning the basis of the motions, and they will interpolate to generate the motions of the Gaussians to model the real-world dynamics. Okay, so let's see some results. Okay, so during training, we also add as rigid as possible constraint to encourage the local motion to be rigid. So this is also a strategy that is utilized in previous approach. Okay, so let's see some. So the left one is the linear Gaussian trajectory without this sparse control points. And the red one is our approach. You can see we can have smooth Gaussian trajectories, and also it also benefits the rendering quality. We can have very sharp rendering qualities, high qualities. This is another example. So this is another example. This is the effect of the as rigid as possible constraints. It also helps us to make the Gaussian trajectories to be smooth to follow real-world motion dynamics. Okay, so this is some qualitative results. I will. So this is the reconstruction result for this dynamic sense. You can see the rendering quality is very high. And I would like to highlight another feature enabled by this spatial representation is that we can enable motion editing. We can create new motions by just replacing this prediction using MLP with user controls. We can allow users to modify the motions and to create new motion patterns. Let's look at the result. So the first row is the result from the conversion from original motion pattern used for training, and the bottom one is the motion editing result that we let users to control the control points and to create a new motion patterns. So this is shown in the bottom. So you can say, although these motions do not exist during training, so the quality of this of the motion sequence is still very high. Okay. Also, the more results go fast. This is the more result. Okay, so I will skip the part. So this is we use this 3D dynamic Gaussians to model casual videos. So we can lift casual video into dynamic 3D Gaussians. This enables a lot of applications. For example, tracking and video consistent depth, and also video editing applications are enabled. Okay, cool. Let's skip. Okay, so besides this reconstruction, we also do some research works relevant to generation with generating 3D objects in order to make the 3D environment to be diversified. So this is one work. I will skip the details. So this is another work that we can compose synthesize the objects into scenes. The texture of these objects are all created. And we can blend add new virtual objects into real world environment. So let's to the conclusion part. So in this talk, I have introduced our works that are trying to convert a casually captured video into a 3D interactive environment. So we have firstly we will extract depth from videos, and then we do surface reconstruction and modeling dynamics of videos. And in the future, there are still a lot of challenges in order to for us to convert a casual captured video into a 3D interactive environment. So this includes that for depth estimation, we would like to have video consistent monocolor depth, and this requires new data and new model for us to have video consistent RGB to RGBD conversion. And secondly, is still 3D representation. Currently, we think we still not have a good representation to model large-scale scene-level reconstruction, surface reconstruction tasks, and also how to simultaneously handle dynamics and static background. Yeah, unified representation is still a problem. Thirdly, the rendering and geometry reconstruction, their trade-off should also be considered in the future. And also, for the casually captured video, the data are imperfect, and the intrinsics and the fixed properties are also unknown. So in future research, maybe there are a lot of research that can be done to uncover material, intrinsic information, and even physics from videos for really to build a 3D simulation environment from videos. And fortunately, we now also have a lot of opportunities. We have large-scale 2D, 3D video generative models, and we have a lot of foundation models that have a good feature utilization capabilities that may offer a lot of opportunities for us to advance this area. Okay, this is the end of my presentations. Thank you. Okay.
Maybe we can send, are you joining us in the panel?
Yeah.
Yeah, that would be good. It will take, due to the interest of time, we'll take the questions in the panel.
Sure.
How about that?
Okay.
Thank you.
Okay.
Any 3D understanding of the world around us, capturing and constructing semantically informed 3D models of the real world, including 3D reconstruction, semantic understanding of community RGB sensors,
Okay, so I think that should now be audio on Zoom. You know, in terms of just applications, we need to understand spatial environments in order to allow machines to be able to also understand these environments. We've been working a lot in terms of 3D reconstruction and then semantic understanding of these kinds of indoor environments. This works, I think, to a nice degree in terms of understanding the 3D scenes. But what we see when we think about, you know, what humans potentially see when they look at 3D is they're capable of looking at something like this image and understanding the general 3D structure. And that means that we have actually very strong 3D priors baked into our perception system because there is not any explicit geometric signal in this image. We have already a general notion of what these kinds of stools potentially look like without seeing the other side or the other side of the kitchen island. And so if we want to help machines be able to perceive this, I want to talk about a slightly different kind of paradigm than probably you've seen a lot of work in terms of computer vision going, which is towards model-based recognition, right? So this is taking a look at, okay, in early kind of robotics, if you want to be able to recognize an object, can you match it from a set of templates that you have available and use that in order to perceive so that we can, of course, then lift to this kind of application. We have data sets like ShapeNet, Objaverse, and such. Can we then retrieve and align a similar object from these kinds of databases and use that to represent the 3D in the scene? And this is also particularly appealing because the objects in these databases are typically human designed. And so they're much more compact and efficient, and they fit well with modern sort of rendering applications, graphics applications, to be able to use these representations. So a very easy way to think about this is to say, okay, if we have correlated pairs between regions of an image and the corresponding 3D shape, we can just learn to match them together with this supervision information. So given some kind of segmentation on the image and the associated 3D shape, we can use a contrastive learning formulation in order to make sure that the similarly structured objects lie close together in a joint embedding space, and different structured objects lie further away, despite them coming from these different domains. And then you can also jointly predict the pose of the objects so that you get the right representation in the space. So when you see a new image, you can just go ahead and do a nearest neighbor lookup in the embedding space, and then find a representative object. So this embedding space looks a bit like this. You see the cluster between different types of structures of objects, like bookshelves and round tables, are actually clustered together differently based on the structure. And that means that we can actually start to do this kind of retrieval-based reconstruction. And if you have good models in your database, you can overcome some of these challenging scenarios, like when you have a lot of occlusions, for instance, in front of this table, or very thin structures in terms of the chair back or the bed structure can be represented just by the nature of the fidelity of these objects. So this is on the Pix3D dataset. It's a simpler retrieval scenario because in the database of 3D shapes associated with Pix3D, you do actually get effectively a ground truth shape that's associated with the observation. It's not a very realistic assumption to make in practice when we want to go ahead and deploy this in terms of 3D perception, since generally speaking, the 3D shapes that we have available, like ShapeNet Objaverse, they're not going to match exactly the kind of stuff that you see in general settings, maybe unless you are IKEA and then have that particular database available. It's not something that we can operate on. So in order to make this more robust and not necessarily overfit to global kind of shape characteristics that are unique to exactly matching settings, you can operate on a patch-based level. So figure out what regions of the image best match what regions of a local 3D shape, and use that in a voting-based strategy to get the most similar kind of shape that represents things. And this also has the side benefit of being much more robust here on the bottom to scenarios where you have occluded objects or objects that go a little bit out of the view of the image. If you operate on a more local patch basis, you can represent those better, as well as the general structure, for instance, on these chairs, which interestingly, I think this does quite well for independent predictions on a per object basis, but clearly when you see these results, you notice that the input chairs are actually all the same. And they're not being represented as the same shape, but that's because they're being independently predicted at the end of this pipeline here with no knowledge of any of the other objects in the scene at that point. So that's something that can certainly be improved in that particular kind of setting. But the nice thing about this patch basis is that you get a much better structured embedding space. If you look at the top 8 nearest neighbors instead of just the top 1, you see that there's a much more similar structure in terms of the shape structure to the input query than if you actually do this masticat approach of associating shape by shape. And that typically tries to memorize one very similar object if it can find one, for instance, the sofa, and then it starts to produce neighbors that are actually very structurally different. Whereas when you do a more patch-based reasoning in terms of finding a similar shape to represent that image, you can get a much better structure in terms of the queries here in the local neighborhood. The thing that I wanted to address a bit more here is that this is actually a monocular perception task, right? Input image to a 3D representation, and that is inherently actually a very ambiguous task in many different kind of ways. So actually, we would much rather have a probabilistic formulation of how to do this CAD reconstruction. In particular, there are depth scale ambiguities in monocular perception, right? The scene can be a little bit larger and a little bit further away, or a little bit smaller and a little bit closer to the camera. And it's inherently ambiguous based on just a single image. The other thing that's nice about having this probabilistic formulation, it helps you with some logistical things, like for instance, that you don't necessarily see the complete object here in the frame of the view. So there's this ambiguity here in terms of the object nature, and also in terms of how to potentially match up objects that don't exactly match, right? So we want a probabilistic formulation to help generalization when we train only on synthetic data, where we have actually good matches and the ability to synthesize a lot of augmentations in terms of data, and then just apply it directly to the real setting. And having this probabilistic model helps to bridge this domain gap here. So our approach here is basically taking an image and producing several different hypotheses of what would potentially explain the CAD reconstruction of the objects that are seen here. So here you see there is a variability in terms of the length of the particular sofa, since we don't see the last bit of it in terms of the image. And if you compose these together, you see that there is some kind of model of the depth scale ambiguity, as some of these explanations are a little bit smaller, closer to the camera, and a little bit further away. So the way that this is captured in a probabilistic setting, we have a decomposition of these different potential ambiguity modalities. So one big thing is depth scale. We operate this on a machine-generated depth estimate. So based on that depth estimate, we're trying to predict the scale that scales it back to its correct true scale. And so that is being modeled probabilistically inherently with a diffusion process. So that allows capturing these different potential kind of modes in terms of the scale offsets that would correct the depth estimate to something that is a correct explanation. And so then we can sample a bunch of different kinds of scales to explain different potential versions of that particular scene being seen through the camera. So once we model the scale, then we can go ahead and model the pose. So this is the machine-generated depth, machine-generated instance mask. If you put these together, you get a partial point cloud of an object that we then use to inform a diffusion model that models the normalized object coordinates associated with these particular object. And so you can also directly just model the object pose as rotation and translation, but it's a much harder distribution to learn correctly, whereas the normalized object coordinates is a much denser information source that then allows us to also solve for the object pose based on the correlation between the normalized object coordinates and the original input point cloud here. And so this helps us to model the potential object poses. And then finally, we want to encode the distribution of shapes in terms of retrieval. So the shapes we can encode through a pre-training process to extract feature representations for all of these shapes. And then based on the condition of the NOx, we can then learn a diffusion process that predicts the actual object latent code here. And this we can then sample and do a nearest neighbor lookup into the trained database in order to get the actual CAD model that represents that shape. So at inference time, this is then going through all of these diffusion models in a cascaded setting. So we take an input RGB image. This is now a real image from ScanNet, and get a machine-generated estimate of the depth and the instance semantics. And so that depth image is going to be fed into the diffusion model that we can then sample different scale estimates from. And then we go ahead and use those scaled depth maps in order to take as input into estimating the object pose and getting out different samples of normalized object coordinates here. And then finally, we can go ahead and estimate the latent codes of the objects for nearest neighbor retrieval, and that produces the final set of object hypotheses that explain this image. And so the interesting thing here is that actually then when we train only on synthetic data, so synthetic 3D front data, we can become more robust than models that have been trained on in-domain data like Roca and Spark, especially in these challenging settings where you see here like the sofa is cut off out of frame. And so there's a much more robust formulation here in our model. The table is a little bit due to data bias in the sense that a lot of tables are happen to be rectangular kind of tables in ShapeNet. So here this lets us more accurately model the round table when we formulate it in a probabilistic kind of fashion. And so here you can see just the alternative 3D representation here. So this is nice in terms of having a really strong prior in terms of the CAD mesh representation, but certainly just retrieving means that you're limited to the set of objects that are actually in the database itself. So we might want to also be able to generate new 3D meshes that would better fit to observations, right? In practice, you know, we talk about these CAD models and these meshes. They are the predominant 3D representation in practical applications, in real world settings. Because you know, they're actually very compact, they're very efficient to render, much faster than pretty much all other representations. From a learning perspective, though, they're very irregular, which makes it extremely challenging to learn. So, you know, we want to be able to actually directly generate 3D meshes, because if you go the route of generating a neural implicit field, which is super nice in terms of, you know, like optimization, because you get gradients through the whole volume, you end up having to run marching cubes. You get out this kind of messy triangulation like this, where you have way too many triangles. And also because of marching cubes, you lose the ability to represent sharp edges, actually. So of course you can go run that through a mesh decimation process. You lose a little bit of the quality there, and you don't quite get the correct tessellation that would intuitively make sense in this setting, which is that the table is actually just a flat plane. So you only really need to represent that as simply as possible. And that's something that you get when you actually learn directly from meshes that have been designed by people rather than by marching cubes. So how can we represent these 3D meshes? I mean, we've all seen the success of sequence modeling and transformers for language. These GPT models are extremely good at modeling text, various different kinds of languages, even code. So we want to be able to leverage that for the ability to generate a mesh, which can be interpreted as a sequence of triangles. It sounds maybe a little bit unintuitive, but it fits into the sequence modeling paradigm, and then we can try to model this with a transformer. So here, when you have a mesh as a sequence of triangles, what we want to learn first is a vocabulary of these triangles, kind of like a vocabulary of words in text generation. And that's being learned on ShapeNet in particular, a shape data set that has these kinds of human design kind of meshes. So we want to encode all of the mesh faces into a dictionary of different descriptions of what mesh faces would look like. So then once we have this trained in terms of a code book of face descriptors, we can go ahead and put this into a GPT-style transformer and train it for, next token prediction or next mesh face prediction styles. And that allows us to do this autoregressive generation of a mesh as a sequence of triangles. The sequence in this case is inspired by Polygen, which shows that actually you can just apply very simple sequence ordering, just in ZYX order, you end up generating a shape in this kind of bottom-up-ish fashion, triangle by triangle, and that can actually produce these nice sort of compact shapes with very sharp edges and features here. So this transformer vocabulary is learned as an encoding on these mesh face features. This is interpreted from a graph convolution, and the features should represent the nodes on, or sorry, the faces should be nodes on this particular graph representation. And then we can extract out these face features. They're going to go through this quantization module to help with the learning process so that faces can learn to kind of snap to each other. Since faces need to fit each other in order to make a mesh look actually coherent. The actual tokenization of face features, you can think about the design in a few different ways. You can potentially have just one global descriptor for that particular face, and then try to generate this. The thing that's interesting about meshes is that they need to have faces that actually stick together, otherwise it's just a complete mess, right? And so there's this very sort of strict structure that vertices do actually get repeated if you're generating faces as a set of triangles over time. And so that structure we can encode directly into the vocabulary as well by saying, okay, actually, faces are going to be encoded as tokens on a per vertex basis. In this case, we have 2 tokens on per vertex. And the whole face feature is just going to be the 6 tokens corresponding to all of these vertices. And that means that when you generate a new face that should actually match with this face, we will see these tokens repeat themselves in the sequence. And that's actually pretty important to get the faces to actually adhere to each other in the generation process, is to structure that vocabulary so that you can easily learn these repetition structures. And so this is, in the end, the face encoding is just the 3 vertices concatenated together into a series of tokens that represent that particular face here. So once these are encoded, we make sure that the decoding can actually reconstruct the original faces so that they encode the sufficient information here. What's interesting here is if you do this without this discretization, the quantization, you get kind of what looks a bit like the face structure of a mesh, but nothing quite fits each other. And so this quantization is important to make sure that we can more easily learn the setting where faces are actually fitting and slotting in with each other. So once that vocabulary has been learned, we can go ahead and just train it with GPT-style transformer to predict what's the next face in a sequence. So here you see the start token of the sequence, the end token of the sequence. We have all of the face encodings in between, and then we just predict what's the next face in terms of that particular sequence. And so when you go through and inference it, you get this nice generation on a triangle by triangle basis. That learns how to generate these kinds of interesting irregular structures that compose an actual mesh representation here. And so if you look at that in comparison also to other works that generate 3D shapes, here you see Polygen is also a mesh generation approach, but it's not an end-to-end learned method. Get3D takes more of the predominant style of learning a neural field and then extracting it with marching cubes. And you also have a couple of other alternative representations for how to represent a 3D mesh in terms of an atlas or in terms of a binary space partition. And here we can generate much more coherent structures in terms of these particular shapes. I think this particular example is nice, a bunch of generated tables, and here we can spend a lot more detail in terms of the table legs versus the top part of the table here as well. I think what's quite nice about this is that actually this transformer-based approach my Zoom just restarted, so I'm gonna just share the screen again. So hopefully that's okay. And so this is, I think, super interesting. And you should check out Yawar at presenting this particular work of his here at CVPR. And it allows us to actually start to generate new interesting 3D shapes. I think there's still an additional question in terms of how we can potentially model really the complexity of these real scenes, right? If we train on databases like ShapeNet or even on Objaverse that has tons and tons of objects, it's not quite the same as modeling the complexity of the scene distribution of what you see in 3D scenes, where you have all this kind of little clutter that makes a real scene look kind of lived in, versus when you see these kinds of real estate kind of posed settings or synthetic data. So there's something a bit missing to really understand the complexity of a real object distribution here. There's certainly a lot, I think, that is to be done for like then saying, okay, well, these are all static scenes. How can we actually model dynamics? In indoor scenes, dynamics usually means what does a person do in terms of an indoor scene, because the people are usually the moving factor behind objects and so on. And so we can try to start modeling the dynamic motion of a person, or even stick that. This is on a per object basis. If the video plays. Maybe. Yes. Okay, so we can do on a per object basis and then just stick that on all the objects in the scene and approximate some kind of interaction with a human scene. Obviously, that's missing this complexity kind of notion of the actual scene configuration, and it won't get you that far in terms of true dynamics. But a lot of the challenge here is actually in terms of looking for data. We don't have a lot of data in the 3D domain, and when you move to the 4D dynamic domain, it becomes even more challenging. And that's where we can start to take inspiration from these very powerful generative image and video kind of models. Learn from that in order to zero-shot interaction generation. So given this text prompt, generate the person on the scene performing that interaction without actually training on any 3D interaction data. And that's purely by leveraging this imaginative power of image generative models. In this case, we're taking a look at stable diffusion in painting models. They're very good at imagining what kind of interactions could occur in an environment. We can ask them to generate various kinds of images of people interacting with their environment, and use that to distill interaction knowledge to produce a 3D version of an interaction in an environment. And what we do there is really just leverage this imaginative capacity and then try to lift it into a 3D consistent setting. So the input is a 3D scene. You have an approximate point location in that scene, and the text description for the interaction you want to generate. You can just render a bunch of images from that location for where that interaction should occur, and then ask the inpainting model to synthesize that interaction, right? So there are a few things to take care for here. If you just do this directly, the inpainting model will rewrite the whole background, which is not great because we want the interaction to be actually consistent with the background. So in order to keep the background context consistent, we actually take the attention according to the token of the person, in this case, the word woman, and use that as a soft guidance for an inpainting mask. This is what this looks like over time of the attention and the inpainting process in order to localize the person such that it's inpainted with the most consistent representation of the background still available. So that gives a bunch of 2D interaction hypotheses. Ideally, we can then optimize for some kind of consistent 3D representation here. One thing to note is that the appearance is still, of course, different. These are generated on an independent basis. We can't expect that the appearance is the same. So we can abstract that information out by just saying, okay, we only want to match the 2D poses. We want our 3D model to match the 2D poses. Obviously, again, these are all generated independently of each other. So the 2D poses are not necessarily view consistent from a 3D setting. However, if we generate a bunch of them, we can expect that actually some of them are going to be consistent with each other in terms of the 3D representation, and that's exactly what we optimize for. So here we're optimizing for a simple body model of the person. These are the pose and shape parameters, and we want to optimize such that it fits with the 2D poses, while allowing for some flexibility in terms of which ones are actually consistent. So we have a variable associated with each hypothesis that will help to downweight inconsistent hypothesis in the optimization so that we're just left with the most consistent set to inform the actual interaction synthesis. And that leaves us with this nice kind of sitting interaction here. So this is very powerful in terms of just raw generality. So we can start to go ahead and imagine kind of things where we have no 3D interaction data available at all, you know, sitting on a cow, picking up weights at a gym and so on. There's no data set that has that kind of realistic information, and this allows us to extend the knowledge of the information out here. Certainly there are a lot of limitations nonetheless. If you look at this cow, certainly the person's fine-grained motion or action here is not quite correct. And that's because we have these different levels of abstraction towards saying, okay, we only want an approximate consistency with the extracted 2D pose. It's a very coarse representation of the interaction, and that's what we can extract out here. But I think this is super promising in terms of starting to inject more generality, and hopefully also bridging this with models that have then been trained on this explicit 3D representation that tells us, you know, what should a good 3D mesh or scene or interaction actually look like. So hopefully that's also interesting in terms of this compositional nature of bringing together general prayers along with sort of true high fidelity kind of 3D data. With that, I would like to conclude and also, you know, can take a few questions if there's actually time. I'm not sure.
Would it not make sense to represent the body, not the body, but the appearance of the body, with some perhaps forgotten model to sort of capture the entirety of the appearance, or you could model the entirety of the mesh with some implicit representation, etc., and then compare the whole image.
Sure, I think in general it makes sense to have something that allows you to get as close as possible to the original image prior, which was trained, you know, on appearance. In this case, we explicitly abstracted that out because we, like with just a pure image generative model, you aren't able to generate a consistent appearance over multiple different independent images. So it's a lot easier to abstract that out. Perhaps I don't think it's an impossible thing to modify the formulation such that you could encourage a much more consistent generation of the appearance over these kinds of images. There are some small kind of logistical things to fight about. So like the pose abstraction helps also with biases that are still baked into image generative models, which is that often it generates the person with a front-facing head. Which kind of sucks when you want to generate lots of different views of a person performing an action, and it tries to force the head into the front-facing configuration. It's something that is sort of easy to bypass by just saying, okay, let's just deal with the pose instead. But I think that is what is necessary if you want to get something that's much finer grained in terms of the interaction understanding. Okay, so the first question, how to handle, let's say, bad meshes, right, with have self-intersections or stuff like this, we don't, because ShapeNet inherently has in its training data lots and lots of self-intersections. So we're just trying to model the data that has been available in terms of what humans approximately have modeled. And that means that, there are already self-intersections, so it is entirely possible to generate meshes with self-intersections. I think this is another challenge as to figure out what are the right kind of loss configurations or supervision signal when you are training on imperfect data in this regard, and trying to encourage, what is really a good mesh. Because there are a lot of things that we can say, ideally it should, be manifold, not self-intersecting and all this kind of stuff. But if you fit together all of these loss configurations into the training paradigm, there are usually still a few edge cases of what can occur that doesn't look quite right in terms of what you want. And I don't know what exactly the right solution is, but it's still certainly important. But I mean, one way to potentially bypass that is just to get a lot of clean data. I don't know how feasible that is at the moment, but it is certainly a lot more difficult to learn when you're learning from already a corrupted set of data. So in this case, the goal was more to say, okay, this is stuff that people have generated. So whatever kinds of characteristics that occur in those meshes are characteristics that we will imitate, for better or for worse. In terms of sequence length, I think this is something that also it's just an inherent thing towards, transformers, LLMs, and stuff like this in terms of understanding better context. There are now some, approaches that have been proposed just for the general language modeling transformer domain, like that potentially allow for a much greater context length. So certainly I think that would probably be applicable in this domain as well. You might imagine maybe also reparameterizing the settings such that it's a bit more semantically informed, because this kind of ZYX sequence generation is not the most intuitive one in terms of how a person would generate an object. But it is, I think, still an important question than how you would define that particular setting, because we don't really have any ground truth information as to how to really separate that out in maybe some kind of better hierarchical, semantically informed approach.
So you talked about but they will be started about it. You can possibly somehow change the context and one of dynamic objects, and would you think that it's possible to extend mesh GPT context one and two?
Okay, so in terms of modeling dynamic objects or modeling humans, I think the main thing is their data. So for humans, that's definitely the case. In fact, then maybe it depends a little bit on what kind of data. So there's a lot of data that is, let's say, represented by a simple model, which is almost too simple to generate because it's the same mesh topology anyways, right? So ideally, you'd like to generate something that is humans that have been modeled by, digital artists that actually have that, because otherwise, if you want to use this to model like Martian cubes meshes, I think you may as well actually just model the implicit fields first, because they're actually very nice to optimize. And there's no reason to try to model like Martian cubes triangles from scratch. But it's mainly, I think, about the data. If you have a sufficient quantity of data, you can also bake in the dynamic information here.
I would want to not just the simple.
Right, but then like the question is, what data is that coming in? If you have a lot of artist created meshes of that style, I think this can be directly transferred to that setting. The thing is, I think a lot of the data that we have of humans enclosed is like captured of real people, which means it's usually like, implicit field Martian cube style kind of meshes, in which case, if you're going to work on that data, it's going to be better to just model the implicit fields themselves, because there's no reason to do this weird roundabout thing of generating then Martian cubes meshes in that setting. By the way, I completely, my bad, left out Yawer on this thank you slide because I copy pasted it from a different presentation, but you should go check out Yawer's Mesh GPT work here at CVPR and also Lei for the interaction synthesis. Yeah, so you can definitely add in an extra condition. I think there's been work that other people have already done to produce a shape conditional version of a Mesh GPT style autoregressive transformer, and it looks like it works quite well. It helps them train on Observers. So, I mean, there's a couple of different ways you can input in that potential kind of condition in terms of whether it's directly in terms of encoded in the sequence or injected in. But I think there's a lot that can be done then in terms of conditional mesh model. So that's what these guys, sorry, I blanked a little bit on the name. I think it's there's already an approach that, because of the shape condition, allows them to train on a lot of different object class categories. I think here you could do it as well. It's just a more complex learning paradigm. You need a lot of examples of the different object classes, of which ShapeNet has really a lot of like chairs and tables and a lot less of everything else. So that makes it a little bit of a logistical challenge if you operate on only ShapeNet kind of objects.
Thank you. I'd like to ask you the panelists, please come to the panel table for and also JM's